What if most of the universe is invisible? Not hidden behind clouds or shadowed by distance, but truly unseen. A silent presence that outweighs everything we can see. Tonight, we're venturing into that mystery. Welcome to the Sleepy Astronomer. If you're new here, this is a calm corner of the internet where we wander through the cosmos slowly, with curiosity and quiet wonder. These videos are made to help you unwind, to ease the mind while still feeding it something beautiful to think about. Where are you watching from tonight? It's always lovely to see how many corners of the world gather under the same night sky. If you enjoy drifting through space in this calm and curious way, please consider giving the video a like and subscribing. It helps more than you might imagine. And to those who are already subscribed, thank you for being part of this quiet constellation of listeners. Hopefully this episode won't be so interesting that it keeps you awake. Though if it does, at least you'll drift off with a little more knowledge about the invisible forces holding the universe together. So settle in, find a comfortable spot, and let's begin. Because tonight we're asking, if we can't see most of the universe, how do we know it's really there? When you look up at the night sky, you see everything the universe chooses to reveal. The glow of stars, the soft smear of a galaxy, perhaps the faint trail of a distant planet. But hidden beneath all that light is something much larger, a kind of cosmic foundation that doesn't shine, doesn't glow, and doesn't reflect. It simply is. This invisible substance, what we call dark matter, outweighs the visible universe by more than 5 to 1. Every galaxy, every cluster of stars, every cloud of gas is suspended within its unseen halo. Without it, galaxies would fly apart, stars would scatter, and the universe as we know it simply couldn't exist. The story of dark matter is one of patient discovery. Astronomers noticed galaxies moving in ways that light alone couldn't explain. They found clusters of galaxies bound together by something unseen, and slowly, piece by piece, the evidence built a picture of a cosmos whose true architecture lies hidden in shadow. Dark matter doesn't block light, it ignores it. It doesn't radiate, reflect, or absorb. Yet through its gravity, it shapes the universe on every scale. It draws galaxies into clusters, sculpts the vast filaments of the cosmic web, and even guides the birth of stars. Throughout this quiet journey we'll trace that story, how we found dark matter, what we know about it, and how it continues to elude us. We'll explore the evidence written in the movements of galaxies, the bending of starlight, and the collisions of clusters. We'll listen to the silence of underground detectors, waiting for a single particle to make itself known, and we'll reflect on what it means that most of existence is invisible. So as you listen, let the pace slow. Let the mind wander among the stars and into the space between them, where gravity whispers and the unseen holds everything in place. Because in the end, the mystery of dark matter isn't just about what fills the universe, it's about what holds it together. In the early decades of the 20th century, astronomy was still stretching its limbs, just beginning to realize how vast the universe truly was. The Milky Way had long been thought to be everything, the full extent of creation, until telescopes grew powerful enough to reveal faint, fuzzy patches of light scattered far beyond its borders. Those smudges were galaxies, whole swirls of stars like our own, suspended in a much larger cosmic sea. It was a revelation that changed how humanity saw itself, no longer the centre of a single island, but a resident of a vast archipelago of universes. It was during this era of discovery that a Swiss astronomer named Fritz Zwicky began to look closely at a gathering of galaxies known as the Coma Cluster. Zwicky was a man of strong opinions and little patience for convention. His colleagues at Caltech often described him as brilliant, unpredictable, and occasionally terrifying to work with. But he had a rare talent for noticing what others overlooked, and in the 1930s he noticed something deeply strange. The Coma Cluster is a collection of thousands of galaxies, each one containing billions of stars, all bound together by their mutual gravity. Zwicky began studying their motion using a technique that was still relatively new at the time, measuring the redshift of light, which reveals how fast an object is moving away or toward us. When he compared the observed speeds of these galaxies to the amount of visible matter within the cluster, something didn't add up. According to Newton's laws of motion and gravity, a galaxy should move within a cluster at a speed that reflects the total gravitational pull of all the surrounding mass. The brighter the galaxies, the more stars they contain and the more gravity they produce, or at least that was the assumption. But Zwicky's calculations showed the galaxies moving far faster than they should have been. So fast, in fact, that by all reasonable estimates the cluster should have torn itself apart long ago. The numbers simply refused to behave. If you added up all the visible stars and gas, you only accounted for a small fraction of the mass required to hold the Coma Cluster together. Something invisible, something massive, had to be supplying the extra gravity. Zwicky called it dunkel Materie, dark matter. It was an extraordinary claim, one that stretched far beyond the comfort of known science. The idea that most of the universe's mass might be invisible was not just unconventional, it was almost unthinkable. Many astronomers at the time considered Zwicky's work an error, or at least an exaggeration. Some joked that he had simply misread the data. Others quietly ignored the problem altogether, hoping it might fade into the background like cosmic static. But the numbers didn't fade. The evidence was there, stubborn and unmoving. The galaxies of the Coma Cluster were racing around at hundreds of kilometers per second, and no amount of visible matter could explain it. It was as though the light from the stars was only the surface shimmer of something much deeper and heavier below. Zwicky himself was not always the best messenger for his own discovery. His personality was as explosive as some of the supernovae he studied. He often insulted colleagues to their faces, calling them spherical bastards, meaning that from every direction they appeared the same. It didn't endear him to many. But behind the bluster was a mind unafraid to confront uncomfortable truths. He understood that if the universe wasn't matching the math, it was the math that would have to bend. Conceptually, the problem was simple enough to grasp. The amount of light didn't match the pull of gravity. The stars alone couldn't account for the motion being observed. Something invisible was adding weight to the cosmos. The light showed only the surface of the universe's story, but gravity was revealing its hidden script. In a way, Zwicky's discovery arrived too early. The tools to verify it didn't yet exist. Telescopes were limited, and computing power was decades away from being able to model such vast systems. So his claim floated through the scientific community like a rumour, intriguing, unproven, and slightly impolite to bring up at conferences. Still, there was something quietly profound about the idea. For centuries, astronomy had been a science of light. Every discovery had depended on what could be seen, from the bright wanderings of the planets to the distant shimmer of galaxies. But Zwicky's data suggested that light was only telling half the story. The universe might be built not of brilliance, but of shadow. Not of what shines, but of what holds the shining things in place. It's easy to imagine him standing under the night sky at Mount Wilson Observatory, looking out across that cold California air, wondering how much of what he saw was real, and how much was merely the outline of something larger. Perhaps he knew even then that his idea would outlive him. Time, as it tends to do, eventually caught up with Zwicky. Decades later, with better telescopes and more refined measurements, astronomers began to see the same strange imbalance everywhere they looked. Clusters, galaxies, even the Milky Way itself, all spinning, all moving too fast for their visible mass. The pattern was universal. Zwicky may not have had the last word, but he had the first whisper, a suspicion that light alone could not account for the weight of the universe. His work became the first crack in a picture of reality that had seemed complete. Science often begins this way, not with a flash of clarity, but with discomfort. The unease of something that doesn't fit, the refusal of nature to conform to our expectations. And while many dismissed Zwicky's dark matter as eccentricity, history would prove him closer to the truth than anyone could have imagined. Even then, long before the term became a cornerstone of modern cosmology, the cosmos was already whispering its secret to anyone willing to listen, that something unseen held the galaxies in place. In the middle of the 20th century, when astronomy was still a world dominated by men and telescopes with glass photographic plates, a quiet revolution began, led not by noise or defiance, but by the steady patience of a woman who simply refused to look away from what the universe was trying to show her. Her name was Vera Rubin. Vera was born in 1928, and from the beginning, her fascination with the sky ran deeper than the night itself. As a child, she would stay awake long after bedtime, watching stars drift across her window frame. Her teachers often dismissed her curiosity about the cosmos as fanciful, a polite way of saying unrealistic, but she persisted, earning degrees in astronomy at a time when few women were given space in observatories, let alone in the faculty halls that controlled them. By the 1970s, Rubin was working at the Carnegie Institution in Washington, D.C., studying something few people thought could yield surprises: how fast stars move around the centers of galaxies. It was, at least on paper, a straightforward task: measure the speed of stars at different distances from the galactic core, and compare those speeds to what gravity predicts. The expectation was simple. In any large spinning system, from a merry-go-round to the solar system itself, the outer parts move more slowly than the inner ones. The sun's gravity keeps the inner planets, like Mercury and Venus, whipping around quickly, while the outer ones drift along at a gentler pace. By analogy, the same logic should apply to galaxies. Stars near the center, where most of the visible mass lies, ought to orbit faster. Those on the outskirts should slow down as the gravitational pull weakens with distance. But when Rubin began measuring, the universe refused to behave. She and her collaborator, Kent Ford, spent night after night collecting data from galaxies like Andromeda, carefully analyzing the spectra, the colored fingerprints of starlight, to determine how fast the stars were moving. What they found was astonishing. The stars far from the center weren't slowing down at all. They were moving just as fast as those near the core, as if the galaxy's outer edges were somehow being pulled along by an unseen hand. If Newton's laws were to be believed, and they had served physics quite well since the 17th century, this made no sense. The only way the stars on the outskirts could move that fast without flying off into intergalactic space was if there was more mass holding them in place. But that mass wasn't visible in any telescope. It didn't glow, didn't reflect, didn't absorb light. It was simply there. When Rubin plotted the data into what became known as rotation curves, the pattern was unmistakable. Instead of dropping off with distance as theory predicted, the curves flattened out, a cosmic signature that every spiral galaxy was enveloped in a massive halo of invisible matter. She double-checked her numbers, then triple-checked. Rubin wasn't the type to chase sensational claims. She was careful, methodical, and relentlessly cautious. She knew how easily an extraordinary idea could be dismissed if not supported by extraordinary precision. And so she worked, patiently, until there was no denying it. The light of galaxies didn't tell the full story of their weight. Her discovery was revolutionary, though Rubin herself delivered it with the humility of someone more interested in truth than glory. She didn't claim to have found a new kind of matter. She simply pointed out that something was wrong with our picture of the universe. Yet the implications were enormous. If her measurements were right, then most of every galaxy was invisible. The delicate spiral arms that fill astronomy books and posters were just the luminous frosting atop an enormous unseen cake of mass. And not just in a few galaxies. In every galaxy studied, the same pattern appeared. The universe was behaving as though some vast transparent substance surrounded every island of stars, providing the gravitational glue that kept them from spinning apart. For astronomers who had grown up trusting the simplicity of Newton's laws, it was deeply unsettling. Either those laws, the bedrock of celestial mechanics, had gone on strike, or something unseen was lending a gravitational hand. The quietness of Rubin's discovery belied its magnitude. She wasn't loud about it. She didn't seek headlines. She published her findings, discussed them in conferences, and let the data speak. Some colleagues resisted the idea, arguing that perhaps she'd miscalculated distances or underestimated the brightness of stars. But the evidence kept piling up. Galaxy after galaxy told the same story. Flat rotation curves, unexplained mass, invisible matter. It's almost poetic to imagine her there, late at night in the observatory, surrounded by machines humming softly in the dark, her eyes fixed on spectral lines that shimmered across the paper like secret messages from the universe. In those patterns of starlight she was glimpsing the true shape of creation, one that light alone could never reveal. Rubin's temperament made her perfectly suited for such work. She once said that science thrives not on answers, but on questions that refuse to die. While others looked for finality, she was content to explore uncertainty. Her calm persistence turned skepticism into curiosity, and curiosity into consensus. Eventually her work became impossible to ignore. Observations from radio telescopes and later from space-based instruments confirmed her findings again and again. It wasn't a fluke or an observational error. It was a new truth. The visible universe is only a small fraction of what's really there. For the first time, astronomers could describe galaxies not as isolated pinwheels of stars, but as glowing centers adrift in halos of dark matter, immense, invisible cocoons stretching far beyond the light we see. These halos, Rubin showed, contain several times more mass than the luminous parts of the galaxies themselves. Without them, the structures of the universe would fall apart. Her quiet revolution reshaped modern cosmology. Dark matter, once a fringe idea muttered by eccentric theorists, became an essential ingredient of the cosmos. It explained not only how galaxies rotated, but how they formed, how they clustered, and how the universe evolved from its earliest moments. And yet, Rubin never stopped finding joy in the simplicity of observation. Each night, she once said, "I go to the telescope expecting to find something new." That gentle optimism carried her through decades of study and into history. though she herself might have found that word too grand for the work she loved. Today her name is spoken with the same reverence given to Galileo or Hubble, not because she shouted to be heard, but because she listened when the universe whispered something unexpected. Her legacy is a reminder that sometimes the most profound revolutions come not with thunder, but with quiet persistence. She didn't just change our understanding of galaxies, she changed how science itself listens to the sky. The image of those spinning galaxies lingers, luminous spirals turning endlessly in the dark, their edges racing faster than light's story can explain. Beneath their graceful arms lies a sea of hidden gravity, a weight that holds them steady against the void. Every spiral galaxy became, in her wake, a kind of lantern surrounded by a vast invisible storm, glowing islands adrift in an unseen ocean of matter that shapes the universe itself. When you zoom out far enough, past the swirling arms of galaxies and the dance of clusters, the universe begins to reveal an astonishing hidden geometry. It's not uniform, not scattered randomly like grains of sand. Instead, it forms an intricate network, a vast cosmic web of threads and knots, where matter gathers along invisible filaments that stretch for hundreds of millions of light years. Between these luminous strands lie enormous empty spaces known as voids, where almost nothing exists at all. This grand structure is one of the universe's most beautiful secrets, and it owes its very existence to dark matter. Though unseen, it provides the skeleton upon which everything else is built. If the visible cosmos, the galaxies, the stars, the clouds of glowing gas, are like the blossoms of a great cosmic tree, then dark matter is its unseen trunk and branches, giving form and strength to what would otherwise drift apart. In the earliest moments after the Big Bang, the universe was astonishingly smooth. The cosmic microwave background, a faint afterglow left from that time, shows only the tiniest ripples in density, differences of less than 1 part in 100,000, and yet those faint ripples were enough. Wherever there was slightly more dark matter, gravity began to draw in additional material. The denser regions grew denser still, slowly gathering clouds of gas and dust that would one day ignite into stars. The emptier regions, by contrast, became even emptier as matter drained away into the growing filaments. Over billions of years, this gentle gravitational choreography sculpted the cosmic web we see today. Galaxies formed where dark matter clumped most tightly, often at the intersections of filaments, places called nodes, where several threads of invisible matter converge. These intersections became the homes of galaxy clusters, enormous cities of stars bound together by unseen gravity. If you could somehow step outside the universe and look back at it, the view would be breathtaking. The dark matter filaments would weave through space like delicate tendrils, branching and intersecting in vast symmetrical patterns. The luminous galaxies would cling to these filaments like dewdrops on a spider's web, marking the points where invisible gravity has drawn normal matter together. Between them, the voids would yawn, immense caverns of near-nothingness, stretching across hundreds of millions of light years. Astronomers have spent decades trying to understand how this invisible web took shape, and in the early 2000s, a groundbreaking project called the Millennium Simulation offered the most detailed glimpse yet. Using one of the world's most powerful supercomputers, scientists recreated a miniature universe within a cube of virtual space over 2 billion light-years wide. They filled it with billions of particles representing dark matter and let gravity run its slow, patient course. The result was astonishing. As the simulated universe aged, tiny irregularities grew into complex networks of filaments and clusters, matching the structure we observe in the real cosmos with almost eerie precision. The galaxies, when inserted into this invisible framework, followed the same grand design, gathering along dark matter's invisible scaffolding, spiraling and clustering just as the universe itself had done. Watching the simulation unfold is a strange experience. It begins as a soft haze, a blur of uniform light. Slowly, faint threads emerge, thin filaments connecting denser knots. Over time, those threads thicken, twisting together into an intricate web that stretches across the entire volume of space. It's as though the universe is growing frost on the windowpane of time, branching outward in silent symmetry. What's remarkable is that dark matter not only shapes where galaxies form, but also determines how they evolve. Without the gravitational framework it provides, galaxies would drift too far apart to collide and merge, a process that drives much of cosmic evolution. Clusters would never gather, stars would never recycle their elements, and the rich diversity of galactic forms we see today, spirals, ellipticals, irregulars, might never have existed. Even though we can't observe dark matter directly, we can trace its influence everywhere. When astronomers map the distribution of galaxies across the sky, they see a faint echo of this hidden scaffolding. Long strands of galaxies stretch between massive clusters, forming bridges that span vast cosmic distances. These bridges correspond to the same filaments seen in simulations, the places where dark matter's gravity has quietly drawn the universe into shape. To study such vast patterns, researchers use what's known as large-scale structure surveys. Projects like the Sloan Digital Sky Survey have catalogued millions of galaxies, allowing astronomers to build three-dimensional maps of the cosmos. When those maps are projected, the patterns are unmistakable. Threads, knots, and voids woven together into something that looks almost alive. The resemblance to biological systems, neural networks, root systems, or even the filaments of fungi spreading through soil is hard to ignore. Nature, it seems, loves to repeat its patterns at every scale. There's something deeply calming about this idea. The same physical laws that guide an apple falling to the ground also orchestrate the dance of entire galaxies across billions of light years. Gravity doesn't rush, it shapes patiently. Over cosmic time it draws matter into balance, a vast and delicate harmony that exists whether we see it or not. Even the emptiness between the filaments plays its part. These voids are not completely empty. They contain the faintest whispers of gas, and perhaps a few lonely galaxies, but their vastness makes the filaments stand out in relief, like the black lines that give shape to a drawing. The contrast between fullness and emptiness, between light and dark, defines the cosmic web itself. It's humbling to realize that this enormous architecture began with the smallest imperfections in an almost perfect early universe. The ripples in density that seeded dark matter's web were minute, yet given enough time and gravity they became the grandest structures in existence. From simplicity arose complexity, from quiet imbalance, beauty. In many ways, dark matter acts less like a thing and more like a framework, a quiet sculptor shaping what can be seen through what cannot. The galaxies are only the ornaments, tracing the deeper design beneath them. Every star, every cluster, every swirling arm of light exists because dark matter provided a stage for it to form upon. And though invisible, this web is not beyond comprehension. Through gravitational lensing, galaxy surveys and simulations, we can map its outlines and follow its threads. We know where the unseen mass lies, even if we can't touch it. The universe, in its vast generosity, lets us glimpse its structure through the motions and positions of the light that it holds. It's a comforting thought, in a strange way, that everything is connected by something we cannot see. The Earth, the Sun, the Milky Way itself, all are beads on the same invisible string, woven into the cosmic tapestry by gravity's patient hand. The universe is not a random sprawl of stars, but a living geometry, stretching across the void in patterns both delicate and immense. And though the threads are unseen, they are what give everything its place. Even in its silence, dark matter has shaped the music of the cosmos, a symphony of galaxies suspended on filaments of the unseen, branching outward like frost on glass, tracing the hidden beauty of a universe held together by what it refuses to show. A century ago, Albert Einstein showed that gravity is not just a force pulling objects together. It is a bending of space itself. Massive things, he said, warp the fabric of the universe, curving the paths of everything that moves through it, including light. It was a radical thought at the time. Until then, light was considered untouchable, pure, straight, and unyielding. But Einstein's equations suggested otherwise. Space bends, and light, ever obedient, follows those curves. The first proof came not from distant galaxies, but from our own sun. In 1919, during a total solar eclipse, astronomers measured the apparent positions of stars near the sun's edge. The starlight had shifted, deflected slightly as it passed through the sun's gravitational field. Space itself had been bent, just as Einstein predicted. It was a subtle change, a displacement barely wider than the thickness of a coin seen from miles away. But it changed the course of physics. That same principle, magnified across the cosmos, allows us to glimpse what can't be seen. When a massive object such as a galaxy cluster sits between us and a more distant light source, its gravity bends the light from that source into new paths. The cluster acts like a cosmic magnifying glass, distorting and sometimes multiplying the background image. Astronomers call this phenomenon gravitational lensing, and it has become one of the most powerful ways to study the invisible scaffolding of dark matter. The effect can be dramatic. In some cases, a single galaxy's gravity bends light from a faraway quasar, a blazing ancient beacon powered by a supermassive black hole, into multiple images. One of the most famous examples is the Einstein cross. Seen through a telescope, it appears as 4 identical points of light arranged in a perfect cross around the center of a foreground galaxy. The quasar behind it is actually just one object, but its light has been split and curved by the galaxy's gravitational field, taking several routes through space before reaching Earth. Each image arrives slightly out of sync, like echoes in time, because the light paths differ in length. It's a remarkable sight. The universe turning its own gravity into a lens, bending the beams of distant light into a kind of cosmic artwork. Where our eyes see repetition, physics reveals geometry, the dance between space, mass, and light. But gravitational lensing doesn't only create spectacular mirages. On a larger scale, it offers something subtler and even more valuable, a way to map the invisible. Most lensing events are not neat or symmetrical. They are small distortions, slight stretches and smears in the apparent shapes of faraway galaxies. If you were to look at a single one of these galaxies, you might not notice the distortion at all. But when astronomers observe millions of them, and analyze their orientation statistically, a pattern emerges, a faint signature of how dark matter is distributed across space. This technique, known as weak gravitational lensing, allows scientists to chart where mass is hiding, whether visible or not. It's a bit like watching sunlight ripple through water. The waves themselves are invisible, but the patterns they create on the pool's floor reveal their presence. Similarly, dark matter can't be seen directly, but it tugs on passing light, bending it ever so slightly, leaving behind a fingerprint of its presence. Telescopes like the Hubble Space Telescope have captured these patterns across enormous stretches of sky. In some deep field images, background galaxies appear subtly elongated, their shapes sheared by the gravitational pull of intervening dark matter. By combining thousands of such measurements, astronomers can reconstruct maps showing the mass distribution across vast regions of the universe. The bright galaxies trace the luminous world, while the lensing patterns trace the unseen one. One of the most striking lensing maps revealed enormous concentrations of dark matter in places where little visible matter exists. These maps confirmed what theorists had long suspected, that dark matter forms the backbone of cosmic structure, the web upon which galaxies hang. Even the most distant clusters, too faint for ordinary observation, can be studied through their gravitational effect on the light that passes by them. There's something quietly elegant about this method. It doesn't demand the universe to reveal itself outright. Instead, it listens to the faint distortions, the small whispers of gravity hidden in beams of light. Each photon carries a story, a memory of the curvature it has passed through. When millions of those stories are pieced together, the invisible begins to take shape. In some rare cases, gravitational lensing produces not just distortion, but magnification so extreme that astronomers can study galaxies from the dawn of time, magnified by nature's own telescope. A cluster of galaxies billions of light-years away can bend and focus light from an even more distant galaxy, brightening it enough for our instruments to see. The result is a glimpse into the early universe, brought into focus by the gravitational pull of matter we cannot directly observe. It's humbling to realize that what makes this possible is the very curvature of space-time, a distortion of geometry itself. In Einstein's picture of the universe, mass tells space how to curve, and space tells light how to travel. When you see a gravitational lens, you're witnessing the interplay of those two commands, the choreography of light across a warped cosmic stage. The mathematics of lensing are intricate, but the essence is simple. Where there is mass, there is bending. Where there is bending, there is knowledge to be gained about what lies unseen. Dark matter reveals itself not by shining, but by shaping the way light moves around it. Astronomers often describe lensing maps as mass portraits of the universe. They resemble weather charts, with peaks and valleys representing concentrations of mass instead of air pressure. But unlike weather patterns, these structures don't drift or fade. They are the fixed bones of the cosmos, the deep architecture of everything that exists. Modern missions such as the upcoming Euclid spacecraft and the Vera Rubin observatory, named fittingly after the woman who revealed dark matter's galactic signature, will expand these maps to an unprecedented scale. They'll measure the shapes of billions of galaxies, creating the most detailed picture yet of the universe's hidden structure. For all the sophistication of the technology, the idea remains delightfully poetic. Light, after all, is the messenger of the cosmos. It travels for billions of years through the silent dark, and in doing so, it records every curve and pull it encounters. By reading those gentle distortions, we learn about the presence of things that have never emitted a single photon. Gravitational lensing has turned the universe into its own laboratory. No mirrors or probes are required, only patience and a telescope sensitive enough to catch the faint bending of starlight. With each observation, we trace a little more of the unseen, filling in the outlines of a map that stretches to the edge of time. It's astonishing to think that, in the end, we come to know dark matter not by its glow, but by its effect on something else entirely. Light bends around it, curves through it, and continues its journey to us, silent proof of gravity's enduring reach. Every distorted galaxy, every mirrored quasar, every subtle smear of starlight is a clue left behind in the cosmos's great puzzle. And when all those clues are pieced together, the pattern becomes clear. Light bends around the unseen, tracing its quiet outlines. In the vast stillness of space, collisions are not explosions in the way we imagine them. They unfold over hundreds of millions of years, more like slow dances than violent impacts. Galaxies drift toward one another, clusters approach clusters, and gravity draws them into brief, delicate encounters that change their shapes forever. Among these cosmic interactions, one has become legendary, a silent crash known as the bullet cluster. It is not just a spectacle of motion, but one of the clearest clues humanity has ever found that dark matter is real. The story begins with two massive clusters of galaxies, each containing hundreds of galaxies bound together by gravity. Around these galaxies floats a sea of hot, thin gas, plasma heated to tens of millions of degrees, glowing brightly in X-ray light. This gas makes up most of the visible mass in the clusters, far more than the stars themselves. When the two clusters pass through one another, the galaxies, spread wide like grains of sand in a desert, barely interacted. They simply kept going, carried by their momentum. But the gas clouds were different. They collided, slowed down, and piled up between the clusters, creating a luminous shock front shaped like a cosmic bullet, hence the name. Astronomers studying this distant scene quickly realized that the visible matter and the gravitational matter were no longer in the same place. The gas, which accounts for the majority of the luminous mass, sat neatly in the middle, exactly where the collision had caused it to stall. But the gravitational pull, measured by its effects on the light from background galaxies, was centered not on the glowing gas, but on the invisible matter that had continued straight through. To see this, astronomers combined observations from multiple telescopes. The Chandra X-ray Observatory captured the searing glow of the gas, while optical telescopes mapped the galaxies and the faint gravitational distortions of background light. Those distortions, a subtle warping known as weak lensing, revealed where most of the mass really was. The results were clear and startling. The galaxies and their invisible halos had surged ahead, leaving the hot gas behind. The luminous and the gravitational were no longer aligned. What this meant was profound. If all the gravity in the cluster came from the visible gas and stars, then the gravitational center of mass should have stayed behind with the glowing plasma. But it hadn't. The gravitational field was strongest where there was no visible matter at all. Something unseen, far more massive than the gas, had passed through the collision unscathed, tugging the fabric of space along with it. This observation created a deep divide between competing theories. For decades, a few physicists had suggested that maybe dark matter didn't exist at all, that perhaps our understanding of gravity itself needed revision. Modified gravity theories like MOND, proposed that the laws of motion might behave differently at galactic scales, producing the illusion of hidden mass. But the bullet cluster presented a challenge that simple adjustments to gravity couldn't solve. No modification of Newton's or Einstein's equations could make the gravitational center shift away from where the visible mass remained. The only consistent explanation was that something invisible, something independent of the gas, carried most of the mass. It was as if nature had staged a perfect experiment, one that no human laboratory could ever hope to recreate. Two clusters collided. The luminous matter lagged, and the unseen matter marched ahead, revealing its presence through the bending of light. The bullet cluster became a cosmic demonstration, an astrophysical experiment written across millions of light years. For scientists who had spent years chasing indirect clues, it was almost poetic. Dark matter had long been a ghost in the equations, a necessary but unseen participant in the cosmic story. Now, for the first time, it had left fingerprints clear enough to convince even the most skeptical observers. When researchers looked closer at the data, they found that the separation between visible and invisible mass was immense, hundreds of thousands of light years. The galaxies, those tiny bright jewels embedded in the cluster, continued mostly unaffected, gliding through space with their halos of dark matter intact. The gas, on the other hand, slammed together, slowed down, and formed a bow-shaped shock wave. The glowing bullet that gave the system its name. The X-ray image from Chandra looked almost painterly, a bright pink cloud of gas, offset from a faint blue overlay representing the dark matter's gravitational map. In that colourful composite, two realities were visible at once, one luminous, one gravitational. The beauty of the bullet cluster lies not only in its clarity but in its timing. The collision happened roughly 150 million years ago, a blink in cosmic time, meaning we are seeing it while the two clusters are still separating. The scene captures the process mid-motion, giving astronomers a rare view of how matter behaves when immense forces meet. This discovery didn't just strengthen the case for dark matter, it transformed it from hypothesis to near certainty. Later studies of other colliding clusters found the same effect. Luminous gas slowed by friction, invisible mass continuing onward. Each one confirmed what the bullet cluster had shown so dramatically, that the universe's true mass is dominated by something that neither collides nor radiates, but simply flows through, shaping the cosmos in silence. There's a quiet elegance in how this evidence emerged. No grand observatory was built for the express purpose of finding dark matter this way. The bullet cluster wasn't designed as an experiment, it was found as one. The universe had written its own demonstration, using galaxies as test subjects and gravity as the measuring stick. When astronomers present images of this cluster, they often overlay the X-ray glow of the gas with the gravitational map derived from lensing. The result is a haunting picture. Two overlapping systems, one of light, one of shadow, forever intertwined. It's not difficult to sense the meaning in it. The visible world drifting apart from the invisible, yet both parts necessary to tell the full story. Even the name carries a kind of quiet poetry. The bullet cluster might sound dramatic, but its motion is measured in mere fractions of light speed, unfolding over eons. It is not violence that defines it, but persistence, the slow, unstoppable pull of gravity sculpting reality. The collision didn't destroy the clusters, it revealed their hidden anatomy. For all its significance, the bullet cluster also reminds us of humility. The discovery doesn't tell us what dark matter is, only that it exists and that it behaves differently from anything we know. It doesn't emit light or heat. It doesn't interact with normal matter except through gravity, and it makes up the majority of all mass in the cosmos. Yet we've only glimpsed its presence through the shapes it carves into the path of light. In that sense, the bullet cluster is both a clue and a mirror. It shows us how science works, how patient observation and the willingness to be surprised can illuminate truths no equation alone could predict. It also shows us something about the universe itself, that it sometimes reveals its greatest secrets not in grand explosions, but in quiet, graceful collisions that speak volumes through their geometry. If you could float near it, 1 trillion kilometers away, watching over the slow-motion aftermath, you wouldn't see anything dramatic. The galaxies would glide by serenely. The gas, hot and faintly glowing, would drift behind like a veil. The true story would be invisible to your eyes, written only in the bending of starlight passing through. Astronomy often deals in metaphors of light, but here the absence of light tells the tale. The bullet cluster doesn't shine brighter than other clusters. It simply shows, unmistakably, that light alone can't describe the universe. Something unseen holds the greater weight, and so, among the thousands of clusters scattered across the sky, this one stands apart. A collision caught mid-breath, its luminous matter lagging behind its invisible twin. In that quiet collision, the universe revealed its hidden bones. When it comes to the mystery of dark matter, the universe has given us the evidence, but not the culprit. We can see its fingerprints in galaxies and its influence on the shape of the cosmos, yet what it actually is remains one of the most elusive puzzles in all of physics. Over the decades, scientists have assembled a sort of cosmic lineup, a handful of suspects that might, in theory, account for the invisible mass holding everything together. None have yet confessed, but each tells a fascinating story of human creativity and curiosity stretched to its limits. The first suspects were relatively familiar, ordinary matter in unusual forms. Astronomers wondered whether dark matter might simply be made of dim, compact objects hiding in the outskirts of galaxies. Brown dwarfs too small to ignite as stars, black holes quietly drifting through interstellar space, or rogue planets wandering without suns. Collectively, these possibilities became known by an appropriately sturdy acronym, MACHOs, short for Massive Compact Halo Objects. For a while, MACHOs seemed promising. They would behave gravitationally like dark matter, and we already knew such objects existed. If enough of them lurked in the galactic halo, they might explain the missing mass without invoking exotic new physics. To test the idea, astronomers turned to a phenomenon called gravitational microlensing, the slight brightening of a background star when a compact object passes in front of it and focuses its light, much like a lens. Throughout the 1990s, dedicated surveys scanned the skies for these fleeting flashes. They did find MACHOs, a few faint stars, some small black holes, even some planet-sized wanderers. But there was a problem. There simply weren't enough of them. The number of events observed was too small to account for the immense gravitational pull attributed to dark matter. MACHOs could explain a fraction of it, but not the bulk. The majority of the universe's invisible weight had to come from something else entirely, something that wasn't made of ordinary matter at all. With the familiar options fading, physicists turned to the realm of the theoretical. The leading idea became that dark matter might consist of entirely new particles, things not yet discovered but allowed, in principle, by the laws of physics. These hypothetical particles would be unlike the ones that make up atoms or light. They wouldn't interact through electromagnetism, meaning they wouldn't absorb or emit light. They'd simply drift through normal matter, pulled only by gravity and perhaps by the weak nuclear force. Thus emerged the most famous candidate of all, the WIMP, short for weakly interacting massive particle. WIMPs became the poster child for dark matter research, not just because of their elegant acronym, but because they fit beautifully into the mathematics of the universe. According to theory, WIMPs could have formed naturally in the early moments after the Big Bang, when the universe was still unimaginably hot and dense. Particles collided constantly, annihilating and creating new forms of matter in perfect balance. As space expanded and cooled, most of those particles disappeared. But if WIMPs existed, their weak interactions would have allowed some to survive, freezing out of the cosmic soup in just the right abundance to match the observed density of dark matter today. Physicists affectionately call this neat coincidence the WIMP miracle. To picture how WIMPs behave, imagine standing in a crowded room full of ghosts. They're everywhere, passing through walls, through you, through everything. Yet you'd never feel their touch. They don't bump into atoms or slow down as they move through the earth. They exist, but almost as if they're made of a different kind of reality. That's the strange beauty of the WIMP hypothesis. Dark matter could be all around us, streaming through your body this very moment, and you'd have no idea. The challenge, of course, is proving it. Detecting WIMPs requires finding evidence of an interaction so rare and so faint that it could easily go unnoticed in a century's worth of data. Physicists have built enormous detectors buried deep underground to shield them from cosmic radiation and everyday noise. These experiments use vats of ultra-pure liquid xenon or germanium crystals, waiting patiently for a single dark matter particle to collide with an atomic nucleus. So far, the detectors have mostly been met with silence, a silence so complete that some physicists joke the WIMPs might have taken their weakly interacting job description too seriously. Each experiment becomes more sensitive, more isolated and more patient, but no confirmed signal has yet been found. Still, hope persists. If even one unambiguous interaction were to appear, it would change our understanding of the cosmos overnight. While WIMPs dominated the conversation for decades, other candidates have quietly gathered intrigue. One of the most elegant possibilities is the axion, a particle proposed in the 1970s to solve a different mystery in quantum physics, the so-called strong CP problem. Axions, if they exist, would be unimaginably light, 1 trillion times lighter than an electron, but they could be produced in such vast quantities that together they might make up the universe's missing mass. Unlike WIMPs, which are heavy and rare, axions would be featherweight and ubiquitous, forming a kind of invisible sea pervading the cosmos. They might occasionally transform into photons, particles of light, under certain conditions, a property that gives scientists a clever way to look for them. Specialized detectors known as haloscopes use powerful magnetic fields and exquisitely sensitive antennas to listen for the faint hum of axions turning into microwaves. So far, no definitive signal has emerged, but the search continues. Then there are the sterile neutrinos. Ordinary neutrinos, those ghostly particles streaming from the sun, and nuclear reactors already barely interact with matter. Trillions pass through you every second without leaving a trace. But sterile neutrinos, if they exist, would be even more elusive, interacting with nothing but gravity. Their existence could explain not only dark matter, but also certain puzzling results in neutrino experiments. If proven real, they would redefine the boundaries of the standard model of particle physics. Some theories venture further still, proposing that dark matter might not consist of particles at all. It could be something more exotic. Primordial black holes formed in the universe's earliest fractions of a second, when density fluctuations were immense. These black holes would be far smaller than those created by collapsing stars, perhaps as light as an asteroid, or as massive as the Moon, yet still dense enough to bend light and shape galaxies. Observational limits make this idea difficult to confirm, but it remains a compelling thought. Perhaps the universe's missing mass is a population of ancient, invisible relics, drifting in the dark since before the first stars were born. The search for dark matter's true nature has become one of the most ambitious collaborations in science. Particle physicists, astronomers, and cosmologists each bring their own tools to the table, from underground laboratories to space telescopes to massive computer simulations. Every approach is a different way of asking the same question. What fills the vast silence between the stars? Despite decades of searching, no single candidate has yet stepped forward with undeniable evidence. Machos turned out to be too few. Wimps remain unseen. Axions are whispering but not shouting, and sterile neutrinos linger at the edge of plausibility. It's as though nature has written the answer in invisible ink, daring us to keep looking. Yet there's a certain charm in the uncertainty. The mystery keeps science honest. It reminds us that not all puzzles are meant to yield easily. The beauty of dark matter research lies as much in the search as in the solution. Each failed detection refines our understanding, narrows the field, and brings us closer to whatever truth waits in the dark. For now, the best we can say is that the universe is full of possibilities. Dark matter could be heavy or light, slow or fast, singular or plural. It could be everywhere at once, gliding silently through galaxies and through us. It could be something we already know, seen from a new angle, or something entirely beyond our imagination. Physicists, ever-patient detectives, continue to sift through the evidence with a mix of rigour and wonder. Their short list of suspects grows shorter, but their curiosity only deepens. And perhaps that's the most fitting way to describe this search. A cosmic mystery with no confession yet. Just a trail of clues leading ever deeper into the quiet heart of the universe. Dark matter, it seems, is still keeping its secret. Or as one physicist once put it with a smile, we know it's guilty of holding the universe together. We just haven't caught it in the act. Deep beneath mountains and mines, far away from sunlight and sound, there are rooms so quiet that the air itself seems to pause. In these hidden laboratories, scientists are listening, not with ears, but with instruments so sensitive they can detect the faintest tremor of energy. What they're waiting for is something that has never been seen, never been touched, and yet may be passing through them by the trillions each second. This is where the hunt for dark matter moves from theory to experiment, where humanity's most delicate detectors try to catch whispers from the unseen universe. The reason these experiments are buried underground is simple but essential. The surface of the Earth is constantly showered by cosmic rays, high-energy particles from distant stars and galaxies that would swamp any attempt to measure something as faint as dark matter. By going deep below the surface, sometimes more than a mile down, scientists shield their detectors from most of this noise. The rock acts as a natural barrier, letting only the most elusive visitors slip through. Down there, surrounded by silence, even the smallest hint of an interaction can stand out. Dark matter, if it consists of weakly interacting particles, should occasionally bump into the atoms of ordinary matter. The impact would be incredibly subtle, like a single snowflake striking the window of a skyscraper. Most of the time, nothing happens, but every so often, perhaps once in many years, a particle might collide with an atomic nucleus, transferring a tiny amount of energy, just enough to be noticed by the right kind of detector. Building such a detector is an act of patience and precision. It must be made from the purest materials on Earth, because even trace amounts of natural radioactivity can mimic the faint signals the researchers are looking for. It must also be cooled to near absolute zero to minimize any background noise from heat or movement. And once it's ready, it must simply wait, listening in perfect stillness for an event that may never come. One of the most famous of these experiments is called LUX, short for the Large Underground Xenon Experiment. It sits inside a former gold mine in South Dakota, more than a kilometer below ground. The heart of the detector is a tank filled with liquid xenon, a noble gas chilled until it becomes clear and dense. When a particle collides with the xenon atom, it produces a tiny flash of light and releases a few electrons. Sensitive photomultiplier tubes surrounding the tank record both signals, allowing scientists to reconstruct where and when the interaction occurred. The beauty of liquid xenon is that it's both heavy and incredibly clean. Its atomic nuclei make excellent targets for dark matter particles, while its lack of chemical reactivity helps eliminate unwanted background signals. Each event is carefully analysed, compared against known types of radiation, and then either catalogued as background noise or flagged as something mysterious. In its years of operation, LUX didn't find a confirmed dark matter signal, but it set some of the strongest limits ever measured, narrowing down where dark matter could be hiding in the particle landscape. Its successor, Xenon-T, operates in a laboratory under Italy's Gran Sasso mountain, using an even larger vat of ultra-pure liquid xenon, roughly 8 metric tons of it. The detector is so sensitive that it can pick up the faint glow of a single photon, yet despite its astonishing capability, it too has been met with profound silence. Each year that passes without a detection helps tighten the constraints, ruling out certain masses and interaction strengths. In science, even silence has meaning. Another key player in the underground search is Super CMDS, located deep inside an old iron mine in northern Minnesota. Rather than liquid xenon, it uses solid crystals of germanium and silicon, cooled to temperatures just a fraction of a degree above absolute zero. When a particle collides with one of these crystals, it produces a tiny vibration, a phonon, and a minuscule electrical charge. Detectors record both signals, providing a double confirmation of any potential event. It's an elegant system, capable of detecting energy deposits smaller than a single billionth of a joule. These experiments operate on scales of patience that would make a monk proud. Years can pass with no clear detection, and yet the scientists remain unshaken. To them, each moment of quiet is a measurement, each unbroken line of data a narrowing of possibility. There's an almost philosophical grace to it, the art of waiting for something that might never arrive, knowing that the absence of evidence still carries weight. One researcher once described the search as trying to catch a snowflake in a hurricane without seeing the snow. The world above is noisy and chaotic. Cosmic rays streak through everything. Particles decay, instruments hum. But underground, in the darkness, the noise fades to almost nothing, and a single, faint touch might just be enough to reveal a new form of matter. In these subterranean chambers, scientists work surrounded by shielding so thick that even the radiation from their own bodies must be accounted for. Some experiments use water tanks or layers of lead to protect their detectors from stray particles. Others rely on computer algorithms to filter out any events that don't fit the profile of dark matter. Every false alarm, a random electron, a neutron from natural decay, a cosmic ray that slipped through, is logged and studied. Each misstep teaches something new about how to listen better. Occasionally an experiment will detect a mysterious signal, an anomaly that hints, for a brief and exciting moment, that dark matter might have knocked at the door. Teams rush to check their instruments, run simulations, and test for background effects. So far, every apparent discovery has eventually been traced back to something mundane: a calibration error, a statistical fluctuation, or a previously unknown source of background noise. It's a reminder that the cosmos rarely gives up its secrets easily, and yet, hope never fades. Every new generation of detectors becomes larger, quieter, and more refined. The upcoming Lux Zeppelin experiment, for instance, combines the lessons of its predecessors into a next-level search, capable of spotting interactions even weaker than those detectable by any prior experiment. Somewhere, the first genuine signal may already be waiting, buried in data, small and easily overlooked, like a single drop of rain on a calm lake. Beyond their scientific purpose, these underground experiments capture something timeless about human curiosity. They show that exploration doesn't always mean launching rockets or building enormous telescopes. Sometimes it means going downward instead of outward, into the earth, into silence, into patience. There's a strange poetry in the idea that, while we look to the stars for answers, some of our most important discoveries may begin beneath our feet. Each time a detector records nothing, that nothing speaks volumes. It tells us how elusive dark matter truly is, how little it interacts, how far beyond ordinary physics it might be. Every refinement, every improved sensitivity, pushes the boundary between the known and the unknown a little further. In a sense, these underground labs are more than just scientific instruments. They are sanctuaries of stillness, places where humanity listens to the quiet hum of the universe, waiting for it to whisper back. There's comfort in the patience of such work. Science, after all, doesn't promise immediate answers. It thrives on endurance, on the slow gathering of evidence, on the idea that progress often hides inside long silences. So the detectors keep listening, the scientists keep watching, and somewhere, perhaps right now, a single particle of dark matter may have brushed against an atom deep below the Earth, leaving behind a faint flicker that will take months or years to find. Because in this search, waiting isn't failure, it's faith in the universe's capacity to speak. Years of silence can still mean progress. Far above the quiet of Earth's underground laboratories, another search for dark matter unfolds. Not in silence, but among the hum of cosmic radiation and the shimmer of distant starlight. Out here, beyond the reach of atmosphere and interference, the hunt continues from orbit, carried out by satellites and observatories that never sleep. They don't dig into the Earth for answers, they listen to the sky. The universe, after all, is a constant symphony of energy. Gamma rays, X-rays, cosmic rays and neutrinos all sweep through space, colliding, scattering and fading into silence. hidden among this chaotic orchestra might be the faint signal of dark matter, not the presence of particles themselves, but the echo of their interactions. If dark matter particles can occasionally collide or decay, they could produce tiny bursts of high-energy radiation. Detecting those flashes would be like catching the universe in the act, revealing the fingerprints of something invisible. The search for these traces has led scientists to turn their eyes towards space. One of the key instruments in this effort is the Fermi Gamma Ray Space Telescope. Launched in 2008, Fermi orbits the Earth every 90 minutes, scanning the sky for gamma rays, the most energetic form of light. These rays can come from all kinds of sources: pulsars, supernovae, black holes, and the turbulent hearts of galaxies. But somewhere among them might be a signal from dark matter. If dark matter particles annihilate when they meet, they could produce gamma rays in specific predictable patterns. Fermi's job is to look for those patterns, especially in places where dark matter is expected to be dense, such as the centre of our Milky Way, or nearby dwarf galaxies that contain little else but dark matter. Dwarf galaxies are particularly helpful because they lack the noisy background of other cosmic phenomena. They're quiet patches of sky where even a faint anomaly might stand out. Over the years, Fermi has found a few tantalizing hints: excess gamma rays streaming from the galactic centre that don't quite match known sources. For a time, it looked like dark matter might be revealing itself. But as always, the universe proved complex. Many of those signals could also be explained by populations of spinning neutron stars or other astrophysical processes. The cosmos rarely gives away its secrets cleanly. It likes to mix wonder with ambiguity. Meanwhile, another experiment has been keeping watch from the International Space Station. The Alpha Magnetic Spectrometer, or AMS-02, is a particle detector about the size of a small car, attached to the station's truss like a silent guardian. It's designed to capture and analyze cosmic rays, high-energy particles arriving from across the galaxy. Among the billions of protons, electrons, and atomic nuclei it measures, scientists hope to find something unusual, an excess of antimatter such as positrons that could be produced by dark matter particles colliding or decaying. The AMS-02 has detected more positrons than expected, sparking waves of excitement in the physics community. Could it be dark matter? Possibly, though other explanations like pulsars releasing energetic particles remain just as likely. The challenge isn't just finding anomalies, it's interpreting them. The universe is a master of mimicry. Signals can overlap, patterns can blur, and data can whisper one thing while meaning another. To make sense of it all, astronomers must separate the cosmic background, the natural chatter of the universe, from the faint orderly notes that might indicate something new. It's an exercise in subtlety, like trying to hear a single heartbeat in a sea of stars. Every data point is scrutinized, every spike or dip measured and remeasured, compared against simulations of what known sources should produce. There's an artistry to it in a way. Each graph and dataset becomes a landscape of possibilities, filled with peaks and valleys where discoveries might hide. The analysts staring at their screens are like astronomers of old peering through telescopes, except their starlight comes in numbers instead of photons. The excitement lies in the smallest details, a tiny asymmetry, a statistical bump that refuses to vanish under scrutiny. Other observatories join this cosmic watch. The Chandra X-ray Observatory, for instance, peers at galaxy clusters and hot gas clouds, searching for X-rays that could result from dark matter interactions. The European Space Agency's integral satellite and Japan's Suzaku mission have hunted for spectral lines, narrow energy signatures that could betray the decay of exotic particles like sterile neutrinos. Each telescope, tuned to its own wavelength, listens to a different layer of the universe's story. The results so far have been mixed but invaluable. The lack of a clear signal tells scientists just as much as a discovery would. It sets limits on what dark matter can be, how strongly it interacts, how massive its particles are, how it might behave. With every silence, the models grow sharper. This is the rhythm of space-based science. Long periods of quiet, broken by the faintest hints of something extraordinary. Researchers must balance skepticism and wonder in equal measure, knowing that the next small fluctuation in data could either rewrite cosmology or dissolve under closer inspection. Yet even that tension has a kind of peace to it. It's the serenity of exploration at its most patient. Imagine the perspective of those instruments orbiting far above Earth, gliding through the darkness as continents drift below. Each one, whether aboard the space station or travelling alone through the void, collects its faint stream of information, while circling endlessly around our fragile planet. From up there, the noise of daily life disappears. Only the deep murmur of the cosmos remains. Back on Earth, teams of scientists translate those signals into meaning, transforming raw numbers into insights about the invisible structure of reality. In the faint hiss of gamma rays and the silent fall of cosmic rays, they search for the story of the unseen. And though they have yet to find a definitive trace of dark matter, their work continues to refine the map of the universe, reducing uncertainty one measurement at a time. It's hard not to admire the sheer scale of patience this requires. The Fermi telescope has been scanning the heavens for more than a decade, recording billions of events, each a potential clue in the grand puzzle. The AMS-02 has logged more than 200 billion cosmic rays since it was installed, its sensors still ticking faithfully with every orbit. If dark matter has a voice, even the faintest one, it's somewhere in that mountain of data, waiting for someone to listen closely enough. There's a quiet optimism behind it all, a shared belief that even the most elusive truths will eventually make themselves known. The universe, after all, has been generous in the past. It has revealed black holes, quasars, and gravitational waves. Perhaps dark matter is simply waiting for us to learn how to listen in the right frequency, or to build an instrument sensitive enough to hear its whisper. Up there, above the blue glow of Earth's atmosphere, the search continues, steady, relentless, and serene. The detectors orbit, the data flows, and humanity keeps its ear pressed gently to the hum of the cosmos. In that endless sea of light and radiation, every photon carries a secret, every anomaly a question, and somewhere, faint and steady, might be the heartbeat of the invisible, pulsing softly beneath the noise of the stars. In the beginning there was heat, not the kind that warms your skin, but the blinding, searing energy of a universe that had just been born. Everything, space, time, matter, and light, burst outward from a single dense state, expanding and cooling in those first moments after the Big Bang. There were no stars yet, no galaxies, no structure of any kind. The cosmos was a thick, glowing fog of particles colliding, merging, and annihilating in a relentless storm of creation. In that primeval chaos, dark matter was already there, quiet, invisible, and strangely aloof. It didn't absorb or emit light, and so while ordinary matter, protons, electrons, and photons, tangled in a blinding web of interactions, dark matter slipped through the melee untouched. It moved under the steady influence of gravity, beginning to gather in tiny unseen clumps, even as the rest of the universe remained too hot and too dense for anything solid to form. As the universe expanded, it cooled. After roughly 380,000 years, the once glowing plasma of particles calmed enough for electrons to combine with protons and form neutral hydrogen atoms. Light, finally freed from constant scattering, could travel across space, the moment we now call recombination. That ancient light still fills the universe today as the cosmic microwave background, a faint radiation that astronomers can still detect with radio telescopes. It is, in a sense, the baby picture of the cosmos. And when scientists look closely at that faint afterglow, they find that it isn't perfectly smooth. Tiny fluctuations, slightly warmer and cooler patches, ripple across it. Those minute differences, less than 1 part in 100,000, are the fingerprints of gravity beginning its slow, patient work. In regions with a little more matter, gravity pulled harder, drawing in more material. In regions with a little less, matter drifted away. Over cosmic time, these tiny irregularities would grow into the grand structures of galaxies and clusters we see today. But gravity's success in shaping the universe wasn't evenly shared. Ordinary matter, despite making up all the visible stuff, stars, gas, planets, and people, played a secondary role. It was dark matter that led the way. Because dark matter doesn't interact with light, it began clumping long before ordinary matter could. While photons kept normal matter suspended in a hot glowing haze, dark matter gathered quietly, forming a vast scaffolding, invisible halos where gravity pooled like water in a landscape. When the universe cooled enough for ordinary matter to fall freely under gravity's pull, it was the dark matter halos that gave it direction. Gas streamed into these gravitational wells, compressing and heating until the first stars ignited. Without dark matter, that process might never have happened, or at least not for billions of years more. The invisible had already drawn the blueprints for the cosmos long before the first points of light appeared. The earliest stars burned hot and brief, living fast and dying in spectacular explosions that scattered heavy elements across the universe. Those elements seeded the next generations of stars, which formed within the same dark matter halos, gathering into the first galaxies. As billions of years passed, those galaxies merged and clustered, tracing out the filaments and knots of the cosmic web. All of this, every star, every cluster, every spiral and elliptical form, followed the contours of the dark matter beneath. It's remarkable how precisely this history can be read in the cosmic microwave background. Satellites like COBE, WMAP, and later Planck have mapped that faint radiation in exquisite detail, revealing patterns that match almost perfectly the predictions of cosmological models including dark matter. The tiny variations in temperature and density in that ancient light are exactly what you'd expect if dark matter were shaping the universe from the very start. They are its indirect fingerprints, preserved in the oldest light we can see. Dark matter didn't just build galaxies, it stabilized them. As ordinary matter cooled into stars and gas clouds, its collisions and radiation would have caused turbulence, scattering material across space. But the smooth, invisible mass of dark matter anchored those regions with gravity too strong to ignore. It provided the cosmic glue, preventing galaxies from dissolving back into chaos. Through billions of years, the same quiet influences continued to guide cosmic evolution. Galaxies orbit one another in groups and clusters that reflect the invisible structure beneath. Even now, the Milky Way drifts within a vast halo of dark matter, extending far beyond the reach of its stars. That halo tethers our galaxy to the cosmic web, gently pulling on neighbouring systems, helping shape the paths of entire clusters as they move through space. To understand how deep this connection runs, imagine the universe as a great symphony unfolding over time. Dark matter sets the rhythm, establishing the underlying beat of gravity. Ordinary matter provides the melody, the bursts of starlight, the glow of nebulae, the sparkle of planets. Without the rhythm, the melody would fall apart. Without the melody, the rhythm would be inaudible. The two together form the harmony of creation. And through it all, the universe has continued to expand. As space stretches, galaxies drift farther apart, carried along by the cosmic expansion, first unleashed in the Big Bang. The light from the earlier stars has been stretched into infrared, then microwave, fading into whispers. Yet even in this cooling and quieting cosmos, the invisible scaffolding remains. Dark matter still shapes the motions of galaxies, still defines the structure of space on the larger scales. It's easy to think of the universe as a story written in light, the glow of stars, the flicker of galaxies, the background hum of ancient radiation. But light tells only part of the tale. Beneath it all lies a deeper narrative written in gravity, one where dark matter is the silent protagonist. It doesn't shine, it doesn't speak, but it gives form to everything that does. When astronomers run simulations of the early universe, adding in dark matter produces a cosmos that looks strikingly familiar, filamentary, structured, alive. Remove it, and everything collapses into bland uniformity. No galaxies, no stars, no planets, no us. The invisible isn't just an accessory to the story of creation, it's the foundation upon which the visible world stands. Over time, the universe transformed from that smooth, glowing fog into a grand tapestry of light and shadow. The first galaxies gave rise to the next, each generation more complex than the last. Clusters and superclusters formed at the intersections of dark matter's threads, shaping the architecture of everything we can see. And though countless stars have burned and died since, the framework that held them has remained unchanged, vast, silent, eternal. It's strange to think that the most abundant substance in the universe is also the one we can't see. But in that irony lies something beautiful. Dark matter reminds us that what's hidden can still be essential, that the forces we never feel directly can shape everything we know. The universe doesn't need to reveal all of itself to be magnificent. The story of cosmic history, from the Big Bang to now, is really a story of collaboration between light and dark, energy and gravity, matter and mystery. The bright galaxies that fill the night sky are the visible expression of a much deeper order, one woven by the unseen threads of dark matter. From the first flickers of light to the swirling galaxies of today, every structure that has ever existed has done so because of that invisible framework. The universe, in all its luminous splendour, needed the invisible to make the visible possible. If you could hold the universe in your hands, it wouldn't look like a sphere of stars or a polished globe of light. It would look like lace, a delicate weave of filaments and voids, galaxies glittering at the intersections like dewdrops caught in a web. And if you could turn that lace in the light, it would shimmer differently from every angle, because most of it wouldn't shine at all. The grand pattern of the cosmos is dominated by something invisible, and yet we can map it with surprising precision. Astronomers have always been map makers at heart. From ancient stargazers charting constellations on parchment, to modern scientists tracing galaxies on computer screens, the impulse is the same: to find order in the infinite. But today's cartographers of the cosmos face a unique challenge. Their subject can't be seen. Dark matter doesn't glow or reflect. It announces itself only through the gravity it exerts. And so the maps they make are built not from light, but from distortion, from the subtle bending of space itself. Modern sky surveys like the Dark Energy Survey and the European Space Agency's Euclid mission are pushing this craft to extraordinary new levels. They don't just photograph galaxies, they measure their shapes, their orientations, and the faint stretching of their light caused by gravitational lensing. When light from distant galaxies travels through space, it passes through regions filled with dark matter. That invisible mass bends the light ever so slightly, distorting the images that reach us. By studying millions of these distortions, scientists can reconstruct where dark matter lies, tracing its distribution in 3 dimensions. It's a bit like mapping wind by watching how grass bends. You can't see the air itself, but you can read its motion in what it moves. The Dark Energy Survey, which observed over 300 million galaxies across 1/8 of the sky, has already created some of the most detailed dark matter maps ever made. These maps show sprawling filaments connecting galaxy clusters, vast empty voids stretching between them, and enormous knots of invisible mass that anchor the cosmic web. Euclid, launched in 2023, is taking the next step. It aims to map billions of galaxies out to distances of 10 billion light-years, creating an immense 3-dimensional chart of the universe's structure. Its cameras can capture incredibly faint galaxies, while its instruments measure their redshifts, tiny shifts in colour that reveal how fast they're moving away as the universe expands. Combining this data will allow astronomers to reconstruct not just where matter is now, but how it has moved and evolved over cosmic time. The result will be a kind of dynamic atlas of the unseen, a portrait of the universe's dark backbone as it stretched and changed across billions of years. When completed, it will help answer one of the most profound questions in science. How did structure emerge from the near-uniform soup of the early universe? Supercomputers play a vital role in this mapping. Even with the best telescopes, we only see slices of the cosmos. To fill in the gaps, scientists simulate the universe itself, starting from the conditions after the Big Bang and letting gravity, dark matter, and dark energy do their work. The Millennium Simulation, one of the first great examples, modelled billions of dark matter particles interacting across a cube of space more than 2 billion light-years wide. More recent simulations, like Illustria's TNG and EAGLE, add baryonic matter, ordinary matter, to see how galaxies and stars form within that dark framework. Watching one of these simulations unfold is strangely mesmerizing. At first, the virtual universe is smooth and uniform, a mist of points scattered in space. Then, almost imperceptibly, clumps begin to form. Filaments stretch outward, pulling matter into strands. Nodes grow where threads meet, forming galaxy clusters. Over time, the cosmic web blossoms into something both mathematical and organic, like frost crystals expanding on a window pane. Each simulation requires staggering computational power. Some take months to run on supercomputers with thousands of processors, each handling a different part of the universe's gravity dance. The results are stored as immense datasets, billions of digital galaxies woven together into models so vast that they too must be explored like worlds of their own. The artistry of this work is difficult to ignore. Though it's grounded in physics and data, there's an undeniable beauty in seeing invisible structure turned into colour and form. Scientists use false colours to represent density and temperature, painting the dark universe in glowing shades of gold, violet, and blue. These visualizations are more than illustrations. They're translations, turning raw mathematics into something the human eye can understand. In a sense, the universe's hidden geometry becomes a kind of cosmic art. The filaments and clusters echo the patterns of rivers and roots, of lightning and veins. It's a reminder that nature repeats itself across scales, weaving familiar forms into unfamiliar contexts. The shapes of galaxies, the tendrils of dark matter, even the empty spaces between, all part of a single, grand composition. Astronomers, in essence, are cartographers of the unseen. They spend their nights not drawing coastlines or mountain ranges, but charting gravity itself. The borders on their maps are defined not by colour or texture, but by the subtle curvature of space. Where light bends, where galaxies gather, where cosmic structures echo the invisible hand that shaped them, that's where they mark their lines. There's a quiet satisfaction in this kind of mapping. It speaks to an ancient human instinct, the need to explore, to trace, to understand where we are. But it also carries a certain humility. Every new survey reveals that the universe is larger, richer, and more intricate than we imagined. Every new map adds detail to the edges of what we know, and expands the horizon of what we don't. For those who work on these surveys, progress is measured not in steps or miles, but in clarity. Each new data set sharpens the picture, turning what was once speculation into structure. The fog of uncertainty lifts a little more each time, revealing that the cosmos isn't random or chaotic. It's patterned, precise, and astonishingly interconnected. And yet even with all our maps, the mystery remains. The outlines of dark matter are clearer than ever, but its true nature is still unknown. It's as though we've charted the shape of a continent beneath the waves without yet touching its sand. The gravitational topography is drawn, but the substance itself continues to elude us. Perhaps that's part of the magic. To map something invisible is to engage in both science and imagination, to see through evidence what the eye never could. It's a form of exploration as profound as any voyage across oceans, only this one stretches across the universe itself. When the data is rendered into 3 dimensions and projected onto a screen, the result looks less like a scientific model and more like a living organism. A vast neural network of galaxies, pulsing with the rhythm of gravity. It's easy, for a moment, to forget that this is the universe we inhabit, that somewhere within those filaments is our own Milky Way, quietly circling its invisible centre. Each map, each simulation, each glowing visualization is a reminder that our understanding of the cosmos is both technical and poetic. Through the patient work of mapping what can't be seen, we glimpse not only the structure of the universe, but something of ourselves, the endless human drive to give shape to mystery. And so, the maps keep growing, the surveys continue, the computers hum in their frozen halls, running the equations that turn gravity into geometry. Piece by piece, the invisible becomes known, or at least known enough to draw. Because even in the age of dark matter and distant galaxies, astronomy is still at heart an act of cartography. A steady hand tracing the unknown, line by line, until the shape of the universe slowly emerges from the dark. When people first hear about dark matter, the imagination naturally runs wild. Something invisible, all-pervading, and powerful enough to hold galaxies together sounds like it ought to be mysterious in a grand, almost mythical way, a kind of cosmic shadow. But science, in its calm and methodical manner, begins not by embracing mystery but by trimming it down. Before we can say what dark matter is, we must first say what it is not. The first misconception is that dark matter might simply be ordinary matter hidden from view, vast clouds of cold gas or dust drifting between galaxies, too dim to see. It's an appealing idea. The universe is full of subtle things, and we're used to discovering that what once seemed empty is simply faint. Yet this explanation doesn't hold. Gas and dust, no matter how cold, still absorb and emit radiation. They glow faintly in infrared or radio light, and sensitive telescopes can detect them. When astronomers measure all the light in every wavelength, from the microwave background to distant radio signals, the numbers don't come close to accounting for the missing mass. The invisible matter we're chasing doesn't interact with light at all. It's not hiding, it's indifferent. Then there are black holes. They seem like the obvious culprits, enormous, invisible, and gravitationally strong. Could the universe be full of tiny black holes, each tugging on nearby stars and galaxies? For a time, this idea, especially the notion of ancient, primordial black holes formed in the first seconds after the Big Bang, seemed plausible. But careful observation has put strict limits on how many black holes of any size could exist without revealing themselves. Their gravitational lensing would bend light in measurable ways. Their mergers would produce gravitational waves that we could detect. The signals we observe simply don't show enough of them to explain dark matter. Black holes may be mysterious, but they are not numerous enough to play the lead in this story. Another source of confusion lies in the name itself. Dark matter often gets mixed up with dark energy, as if the two belong to the same family. They share the word dark only because both are invisible. Otherwise, they are entirely different phenomena. Dark matter pulls with gravity, helping galaxies and clusters stay bound together. Dark energy, on the other hand, pushes, driving the accelerated expansion of the universe. One gathers, the other separates. It's an elegant cosmic irony that both the universe's cohesion and its expansion depend on things we can't see, but their effects point in opposite directions. So if dark matter is not gas, not dust, not black holes, and not dark energy, what's left? That's the heart of the puzzle, a mystery defined more by elimination than by identification. Science, contrary to its popular image, is often less about eureka moments and more about gradual refinement. Discovery can feel a lot like sculpture. You start with a block of marble, a rough, unformed idea, and with every experiment, every observation, you chip away at what doesn't belong. Slowly, the contours of truth begin to emerge. This process has ruled out plenty. Dark matter doesn't behave like ordinary matter. It doesn't clump into stars, it doesn't heat up, and it doesn't form complex chemistry. It passes through everything without friction, ignoring electromagnetic forces entirely. It's as if the universe contains a hidden population of particles living in a parallel gravitational world, occupying the same space, but never touching ours. Even so, we have to be careful not to mistake absence for failure. Every eliminated possibility tightens the frame. Knowing what dark matter isn't allows physicists to focus their searches more precisely. Narrowing down the range of potential masses interactions and formation histories. The silence from underground detectors, the lack of telltale signals in space, the missing flashes of gamma rays or X-rays, all of it, strangely enough, counts as progress. Sometimes the process is unexpectedly poetic. Astronomers use the same telescopes that reveal newborn stars and dying galaxies to map the voids between them, tracing where dark matter must lie. Particle physicists build enormous instruments, cool them to near absolute zero, and listen for collisions that never seem to happen. Each quiet night of data adds another chip to the marble block. Science, in its most patient form, is as much an act of listening as it is of looking. It's worth remembering that ruling things out has always been part of discovery. The atom was once thought indivisible, until experiments chipped that certainty away. The universe was once believed static, until galaxies were seen racing apart. Progress, especially in cosmology, often comes from subtraction, peeling back layers of assumption until what remains, however incomplete, finally fits what nature is whispering. And sometimes those whispers take decades to interpret. When the first hints of missing mass appeared in galaxy clusters, no one believed them. When Vera Rubin's rotation curves confirmed that galaxies were surrounded by invisible halos, it still took years for the idea to sink in. Even now, with evidence spanning from cosmic scales to subatomic experiments, dark matter remains defined as much by mystery as by measurement. This ambiguity doesn't bother most scientists. If anything, it fuels them. Knowing that the universe contains something so abundant yet so quiet is less frustrating than it is invigorating. It means there are frontiers left, realms where imagination and mathematics meet reality in delicate balance. It's a reminder that even in an age of satellites and supercomputers, nature still holds secrets beyond the reach of our instruments. When researchers talk about dark matter today, they do so with both confidence and humility. Confidence, because its gravitational effects are undeniable. Humility, because every test that fails to reveal it is a gentle nudge from the universe, urging patience. The search is less about chasing a final answer than about deepening understanding. Each non-detection is like the pause between notes in a symphony, silent but meaningful. And so, for now, dark matter remains defined by what it is not. It's not the familiar matter of stars or planets. It's not the luminous gas between galaxies, nor the compact remnants of dead stars. It's not even the mysterious energy pushing the cosmos apart. What's left is a quiet gravitational presence, unseen, untouchable, and still waiting to be understood. That might sound unsatisfying, but there's a certain beauty in it. The universe rarely gives up its mysteries all at once. Sometimes it lets us circle the truth for generations, carving slowly, revealing a shape that was there all along. The search for dark matter, then, is not just about filling a gap in physics. It's about learning to appreciate the elegance of the unknown. The same curiosity that led early astronomers to map the stars now leads us to map the voids between them. The difference is that this time we're charting a landscape made of silence. And perhaps that's fitting. After all, the universe began in darkness before there was light. It has always been the unseen that gives form to the visible. Each unanswered question keeps the conversation going, reminding us that knowledge is not a finish line but a horizon that moves as we approach it. We know what dark matter is not. We know it leaves no glow, no trace of chemistry, no warmth or shadow. And yet, by ruling out so much, we've inched closer to the truth that lies beneath. What remains is possibility and patience. if dark matter is the universe's quiet sculptor, drawing galaxies together, shaping structure, holding stars in graceful orbits, then dark energy is its great counterpoint. Where dark matter gathers, dark energy separates. One builds, the other unravels. They are two invisible forces acting in perfect opposition, the yin and yang of cosmic balance. The story of dark energy begins with an old assumption. For most of human history, people believed the universe was static, unchanging, eternal, a fixed stage upon which celestial dramas played out. Even Einstein, when he developed his theory of general relativity in 1915, expected that gravity's pull should eventually make the cosmos contract. To keep the universe from collapsing under its own weight, he added a term to his equations, the cosmological constant, a mathematical adjustment to hold everything in place. But in 1929, astronomer Edwin Hubble peered through his telescope and made a startling discovery. Galaxies were not drifting randomly through space. They were all moving away from each other, the more distant ones receding faster than the nearby ones. The universe, it seemed, was expanding. Einstein's cosmological constant was suddenly unnecessary, even embarrassing. He reportedly called it his greatest blunder, though time would have the last laugh on that point. For decades afterward, astronomers assumed the expansion of the universe must be slowing down. Gravity, after all, is a universal attraction. Over billions of years, it should gradually pull things back together, or at least ease the rate of expansion. But in the late 1990s, two independent teams studying distant supernovae found something entirely unexpected. The universe wasn't slowing down, it was speeding up. Galaxies were racing away from one another faster and faster, as if some invisible pressure were pushing everything apart. That mysterious pressure became known as dark energy. No one knows exactly what it is, but its effect is unmistakable. It acts not like matter, which clumps and collapses under gravity, but like an intrinsic property of space itself, a smooth, uniform energy that fills the cosmos and drives it to expand ever more quickly. If you imagine the universe as a vast fabric, dark matter would be the threads that weave patterns and knots, while dark energy would be the tension that stretches the cloth. One pulls together, one pushes apart. Their competition defines the universe's fate. Today, astronomers estimate that roughly 68% of the universe is dark energy, 27% is dark matter, and only about 5% is ordinary matter, everything made of atoms from planets to people. That means nearly all of existence is governed by two forces that cannot be seen or touched. It's an almost philosophical revelation. Everything familiar is just a trace, a glimmer of the true cosmic balance playing out on scales too vast to comprehend. Dark matter's gravity keeps galaxies and clusters bound, preventing them from flying apart. Dark energy, by contrast, acts on the larger scales, pushing the fabric of space to stretch faster with time. For billions of years, dark matter's pull dominated, allowing galaxies to form and structure to grow. But as space expanded, dark energy's influence grew stronger. Eventually, its repulsive effect began to win. To picture this, imagine tossing a handful of glitter into the air. For a moment, gravity gathers it, slowing its motion, pulling it downward. But then imagine an unseen wind gradually picking up, lifting and scattering the glitter until it drifts apart forever. That's the universe's long game, a tug of war between the pull of dark matter and the push of dark energy. The exact nature of dark energy remains deeply uncertain. Some scientists think it might be Einstein's cosmological constant resurrected, a fundamental property of space that exerts a constant outward pressure. Others suspect it could vary over time, driven by an unknown field dubbed quintessence, an echo of ancient philosophy where the fifth element beyond earth, air, fire, and water was something ethereal and perfect. Observations of the cosmic microwave background, galaxy distributions, and supernova distances all point toward the same unsettling conclusion. The expansion of the universe is not only accelerating, but doing so in a way that fits no simple pattern. It's as if the universe has a built-in tendency toward emptiness, an energy of nothingness that grows stronger as space itself grows larger. There's a poetic irony in that. When cosmologists first measured how much matter exists in the universe, they expected gravity would one day bring everything back together. Now, the data suggest the opposite, that gravity's triumphs, the galaxies, the clusters, the stars, are temporary sculptures in an ever-expanding stage. The cosmos may never collapse. Instead, it may stretch itself thinner and thinner until distant galaxies slip beyond visibility, their light red-shifted into silence. And yet, there's no need for gloom in this picture. The universe has always been a balance of creation and dissolution. The same expansion that scatters galaxies also creates the conditions for stars to form, for elements to fuse, for life to exist. Without the precise equilibrium between gravity's pull and expansion's push, the cosmos might have collapsed too quickly or expanded too fast for anything stable to arise. We exist in a moment of perfect tension, a universe not yet torn apart but still held delicately together by invisible hands. These two forces, dark matter and dark energy, coexist like partners in a cosmic dance. For billions of years, dark matter's gravity built structure, gathering gas into galaxies and galaxies into clusters. Then, as the universe aged and space itself expanded, dark energy's influence grew. Now it leads the dance, stretching the cosmos faster than gravity can pull it back. Neither dominates completely. Together, they choreograph the grand evolution of everything. Astronomers have a certain fondness for this symmetry. There's something deeply satisfying about the idea that the universe's two greatest mysteries mirror each other. One attractive, one repulsive, one local, one global. It's as if the cosmos itself maintains a sense of balance, a gentle reminder that even opposites can coexist in harmony. The search to understand dark energy is as ambitious as any quest in modern science. Observatories like the Dark Energy Spectroscopic Instrument and the Vera Rubin Observatory are mapping millions of galaxies to measure how fast they're moving and how their distribution changes over time. These vast datasets might reveal whether dark energy truly is constant, or if it evolves, fluctuating like a pulse in the fabric of space. Whatever its nature, dark energy challenges some of our deepest intuitions. It suggests that emptiness isn't really empty, that the vacuum of space has an energy of its own, a quiet pressure that shapes the destiny of everything. It redefines nothingness as something dynamic, alive, and essential. Even Einstein's so-called blunder may not have been one after all. His cosmological constant, once dismissed, now seems remarkably prescient, a term waiting patiently in his equations for the universe to prove it right. The more we study dark energy, the more it humbles us. It forces us to accept that what we perceive as the grandest structures, galaxies, clusters, even the cosmic web, are only temporary patterns in an expanding sea. The future may belong not to stars and galaxies, but to the quiet, accelerating emptiness between them. And yet, that future doesn't diminish the wonder of what exists now. The night sky remains a living record of this balance, every star a product of gravity's pull, every stretch of blackness a reminder of expansion's push. It's a universe forever poised between cohesion and dispersal, between the impulse to gather and the urge to let go. Two invisible hands shape everything, one holding, one releasing, and so the cosmos continues its delicate equilibrium, expanding, evolving, unfolding, not rushing toward an end, but drifting gracefully between two silent forces, forever balanced between what binds and what lets go. Imagine for a moment that dark matter could shine, not brightly, not in blinding streaks like the stars, but with a faint, quiet light of its own. The universe would be transformed. Every familiar constellation would blur into a background tapestry, and the blackness between stars would no longer be black at all. The whole sky would glow with a soft luminescence, revealing the true architecture of the cosmos, an enormous web of filaments stretching across space, each thread shimmering like mist in the starlight. If dark matter glowed, galaxies would no longer seem like isolated islands. Each one would be wrapped in a vast halo of diffuse light, extending far beyond the visible spiral arms. The Milky Way would appear as a bright core surrounded by an immense sphere, a cosmic lantern adrift in a luminous sea. From our vantage point, it would look almost like a jellyfish of light, its tendrils reaching into the dark, merging seamlessly with the halos of nearby galaxies. The local group, our small cluster including Andromeda and dozens of dwarfs, would be connected by soft, glowing bridges. What now appears as emptiness between galaxies would reveal itself as structure, elegant, continuous, alive. Across the larger universe, the view would be breathtaking. The cosmic web, which we currently infer from simulations and gravitational maps, would become visible in all its complexity. Long filaments of light would lace across the night sky, connecting clusters separated by millions of light years. The densest nodes, where the strands intersect, would blaze faintly brighter, the hidden hubs of dark matter where galaxies gather. Between them, immense voids would remain dim, tranquil expanses framed by glowing borders, like the negative space between strokes on a canvas. The scale of this light would be beyond anything human eyes could grasp. Even if dark matter emitted just a whisper of radiance, its sheer abundance would make the sky look alive. Not a field of dots, but a woven tapestry. Every direction you looked would hold structure, texture, and motion. The concept of empty space would vanish. The universe would resemble a living organism, bright threads feeding luminous clusters, a pulse of light flowing through cosmic veins. In this imagined universe, time itself would seem to breathe differently. You could watch the slow drift of brightness as galaxies moved along dark filaments, drawn together over billions of years. Clusters would appear to shimmer gently, their halos swelling and merging. The large-scale structure of the cosmos, normally invisible to us, would play out like a quiet cosmic ballet of light and gravity. Even our own sky would change. On a dark night far from cities, instead of a thin band of stars we call the Milky Way, the entire dome of the sky would be softly luminous. The familiar constellations would dissolve into a diffuse glow, their outlines replaced by vast, gentle gradients of light. If you stood outside beneath this glowing web, the horizon would feel infinite, the sky more ocean than vault, A softly shining sea with no shore. The brightness wouldn't flicker or flare like stars. It would be steady, serene, the kind of glow you could almost feel rather than see, like moonlight filtered through water. It might even change the way we think about darkness itself. There would be no true blackness, no void between worlds. Everywhere, even in the deepest corners of intergalactic space, the faint pulse of dark matter's light would linger, a constant reminder that nothing is ever truly alone. The view from deep space would be even more remarkable. Imagine drifting between clusters, surrounded not by emptiness but by glowing filaments that extend in every direction, as though suspended inside a vast cosmic web. The filaments would stretch farther than imagination can follow, fading gradually into distance without ever quite ending. Stars, galaxies, and even the rare wandering planet would be secondary details, decorations within a greater pattern. You would feel as though you were floating inside the skeleton of the universe itself, tracing the framework that has shaped everything since the dawn of time. From the perspective of a telescope, the cosmos would no longer look like a field of scattered galaxies, but like a vast, interconnected structure, almost architectural in its design. The outlines of dark matter's invisible filaments would define the true shapes of galaxy clusters, showing how they gather and grow. Astronomers wouldn't need to infer their existence from gravitational lensing or simulations. They could simply see them, faint and steady, stretching across the depths of space. If dark matter emitted light, we might even perceive the passage of time differently. Watching the universe evolve would be like observing the slow blooming of a flower. The filaments would expand and thin as the cosmos aged, their glow dimming as galaxies drifted apart. The great clusters, the bright nodes of the cosmic web, would shine for billions of years, their light tracing the last great gatherings of matter before dark energy's expansion carries everything too far to connect. Even our understanding of beauty would shift. The night sky, once a symbol of isolation, would become a vision of connection. Every point of light would be linked to every other, part of an unbroken web binding the cosmos together. There would be no true edges, no lonely stars adrift in nothingness, only continuity. The universe would seem less like a collection of separate objects, and more like a single vast entity, glowing softly with its own inner harmony. It's fascinating to think that this imagined view isn't far from the truth, only hidden from our eyes. The shapes, the filaments, the clusters all exist. We simply can't see them. Our instruments can trace their gravity. Our simulations can recreate their form, but the actual sight remains veiled. The invisible architecture is real, and it dwarfs everything we can observe directly. There's something humbling about that thought. The night sky, as magnificent as it is, only shows the surface layer of reality, the luminous frosting on a much deeper cake. What we call darkness is not an absence of structure, but a presence we cannot yet perceive. The stars shine, but it's the unseen mass around them that defines where they can be. The light gives us beauty, but the dark gives us form. If one could glimpse even a fraction of that hidden light, astronomy would feel more like art than science, the study of cosmic texture, the mapping of harmony itself. Every telescope would be a painter's brush, capturing the soft, intricate glow of gravity's handiwork. The universe would be a masterpiece revealed, not cold, not empty, but exquisitely alive. and perhaps in some far future we might invent instruments that make this vision possible, not by giving dark matter literal colour, but by translating its gravitational presence into light our eyes can see. To gaze upon that would be to see the universe as it truly is, a vast web of connection, where every galaxy is a bead on a thread of invisible brilliance. Until then, we look up into what seems like darkness, knowing that beneath that black canvas lies an unseen light. The cosmos is not empty, it's simply quiet about its fullness. If dark matter had light, the night sky would never look empty again. Science, for all its confidence and precision, thrives on doubt. Every great discovery begins with someone raising an eyebrow and saying, "Wait a minute, what if we're wrong?" The story of dark matter is no exception. While most astronomers are convinced that some form of invisible mass shapes the universe, a persistent minority wonders whether the mystery lies not in hidden matter at all, but in the laws of gravity themselves. After all, if your calculations don't match reality, perhaps the problem isn't with the universe. Perhaps it's with the math. That idea, bold and controversial, gave rise to one of the most fascinating alternatives in modern astrophysics: MOND, or Modified Newtonian Dynamics. The concept was first proposed in the early 1980s by Israeli physicist Mordechai Milgram, who noticed something curious about the way galaxies spin. When stars orbit the centres of their galaxies, they move faster than Newton's laws predict. The standard explanation, of course, is that an invisible halo of dark matter provides the extra gravity needed to keep them from flying apart. But Milgram suggested a different possibility, that maybe Newton's laws themselves start to behave differently at very low accelerations. In everyday life, Newton's laws work beautifully. Apples fall, planets orbit, satellites behave exactly as predicted. But in the outskirts of galaxies, where gravitational accelerations are unimaginably weak, trillions of times smaller than what we experience on Earth, perhaps gravity doesn't fade as quickly as expected. Milgram proposed that at these scales gravity might strengthen just enough to account for the fast orbital speeds of stars without invoking any unseen matter. In other words, maybe there's no ghostly mass after all, just a subtle quirk in the fabric of gravity. The idea was daring, even heretical, but it had a strange elegance to it. Mond could explain galaxy rotation curves, the very phenomenon that first hinted at dark matter, with remarkable accuracy. When plotted against real data, Milgram's equations often fit better than traditional models. It was as if the universe itself were whispering, "You're close, but not quite right about how gravity works." Still, Mond faced problems. It worked beautifully on the scale of individual galaxies, but it struggled with larger systems like galaxy clusters, where even its modified gravity couldn't account for all the observed effects. It also clashed with Einstein's theory of general relativity, which has passed every experimental test so far. And while Mond explained some things neatly, it couldn't easily account for others, like the gravitational lensing of light around clusters, or the cosmic microwave background, both of which align strongly with the existence of dark matter. Over time, theorists refined Mond into more complex frameworks. One of the best known is TVS, tensor vector scalar gravity, a relativistic extension that tries to merge Milgram's ideas with Einstein's geometry of space-time. Others have explored emergent gravity, an approach suggesting that gravity itself might arise from microscopic quantum interactions, rather than being a fundamental force. Each of these theories shares a common thread: the belief that dark matter may not be missing at all. it might simply be a misunderstanding of how gravity behaves when stretched across the vast scales of the cosmos. The appeal of these theories isn't stubbornness, it's the scientific instinct to question the obvious. For all its successes, the dark matter model has a glaring hole. We still haven't found the particles that make it up. Decades of searching have revealed no WIMPs, no axions, no sterile neutrinos, no signals of any kind. It's entirely reasonable then to ask whether the universe is truly filled with invisible matter, or whether our gravitational equations are incomplete. And in fairness, Mond and its relatives have scored some impressive points. They can predict the detailed behaviour of galaxy rotation curves using only visible matter, something dark matter models often have to adjust for with flexible assumptions. That precision earns Mond genuine respect among a subset of astronomers. It's as though Newton's old laws still work, but only after being ever so gently retuned for the faint edges of galaxies. However, the weight of evidence still leans toward dark matter. Observations like the bullet cluster, where visible gas and gravitational mass separate after a cosmic collision, are hard to reconcile with modified gravity alone. Likewise, the large-scale structure of the universe, as seen in cosmic surveys and simulations, matches dark matter's behaviour almost perfectly. The patterns of galaxy clustering, the anisotropies in the cosmic microwave background, the way light bends through massive clusters, all of it fits beautifully under the dark matter framework. Still, the alternative theorists remain important. They remind the field that explanations, however elegant, must stay accountable to observation. Their questions keep cosmology honest, forcing every model to earn its certainty through evidence. Science, after all, isn't a temple of fixed truths. It's a workshop full of blueprints being constantly redrawn. What's fascinating is how these debates often overlap rather than contradict. Many physicists see Mond not as a replacement for dark matter, but as a clue, a mathematical echo that might point toward deeper physics. Perhaps the laws of gravity do change slightly at cosmic scales, but dark matter still exists alongside those effects. Or perhaps dark matter itself interacts in subtle ways that mimic the tweaks Mond describes. The truth may lie somewhere in between, waiting for both camps to meet halfway. Even Einstein, whose theories underpin nearly everything in modern cosmology, would likely smile at this uncertainty. He once said that the more he studied the universe, the more humble he felt before it. The greatest minds in physics have always been willing to admit that their understanding is provisional, beautiful, consistent, and yet still incomplete. There's also a human side to all of this. The scientists arguing for or against dark matter aren't adversaries. They're collaborators in the grandest experiment of all, figuring out what the universe is made of. Some dig deep into underground detectors, others stare at the stars through space telescopes, and others still play with equations that might rewrite the laws of nature. Their disagreements aren't signs of division. They're the sound of discovery in motion, and there's a kind of humility in the fact that, after centuries of studying gravity, from Newton's falling apples to Einstein's bending space-time, we still don't fully understand it. The force that holds our feet to the ground, that keeps planets in orbit and galaxies spinning, remains mysterious when stretched to cosmic proportions. Even gravity, it seems, enjoys keeping us on our toes. These alternative theories serve as a reminder that science advances not only by confirming ideas, but also by challenging them. Every time an experiment fails to detect dark matter, the possibility that gravity itself holds the key grows just a little stronger. Every time new data fits perfectly with dark matter predictions, Mond is forced to evolve. The two viewpoints push each other forward, sharpening the edge of what we know. And perhaps in the end, that tension is what matters most. Whether dark matter is a sea of invisible particles or simply a quirk in the cosmic rules, the search keeps humanity reaching outward. Not just for answers, but for better questions. There's comfort in that. The mystery remains open, the debate alive, the curiosity unbroken. In the grand workshop of the cosmos, there is still room on the chalkboard, still space in the equations, still silence in the data waiting to be filled. One day, perhaps, we'll discover whether the universe truly hides its mass in shadowy particles, or whether gravity itself bends the rules more than we imagined. Until then, we balance between evidence and imagination, between theory and wonder, forever listening to the quiet argument of the cosmos. Across the depths of the universe, everything moves. Galaxies spin, clusters drift, and filaments stretch between them like threads in slow motion. Yet all of this motion, every orbit, every collision, every graceful spiral, is choreographed by something unseen. Beneath the bright notes of starlight lies a deeper, quieter rhythm, the pull of dark matter, shaping the cosmic dance. If you could watch the universe unfold from above, not for minutes or years, but over billions of years, you'd see a kind of silent symphony playing out. Galaxies would whirl like instruments in an orchestra, each moving not in isolation, but in harmony with a greater pattern. Their orbits would trace invisible curves within halos of dark matter, bound by gravity's tempo. Around them, clusters would glide along vast filaments of unseen mass, converging at cosmic intersections before drifting apart again. Dark matter gives this symphony its rhythm. It sets the beat that everything else follows. Where dark matter gathers, its gravity deepens the tone, pulling in gas and stars to form galaxies. Where it stretches thin, the melody softens. Space expands, and light travels freely through the gaps. Even the grandest movements of the cosmos follow its pulse. Astronomers describe galaxies as residing within halos of dark matter, enormous spherical envelopes extending far beyond the visible disks of stars. These halos are the true anchors of cosmic motion. Without them, galaxies would simply spin themselves apart. The stars at their edges, moving far too quickly for the visible mass to contain them, owe their graceful orbits to the invisible mass surrounding them. Each galaxy's motion is like a melody woven into the deeper harmony of its halo. When these galaxies cluster together, their halos overlap and merge, creating massive gravitational wells that bind hundreds or thousands of galaxies in a single system. The Milky Way itself is part of one such cluster, the local group, drifting within a larger web of structures known as the Laniakea supercluster. The entire system is in motion, flowing like notes along the strands of dark matter that connect the universe's great structures. Every movement from the spin of a star to the drift of entire clusters is part of this vast, unbroken arrangement. If you could somehow see dark matter's influence, it would look like a web in motion. Not static, but alive. Filaments would twist as clusters slide along them, the cosmic web flexing under the weight of its own gravity. Over immense spans of time, these filaments would stretch and shift, forming bridges between clusters and feeding new galaxies along the way. It's a slow, cosmic ballet. Matter drawn inward along invisible corridors, moving always toward deeper notes of density. The analogy to music is more than poetic. It's almost literal. Gravity has a rhythm. In clusters, galaxies orbit their common center like instruments tuning to the same key. Some move fast, their trajectories sharp and complex. Others drift slowly, resonating with deeper gravitational tones. Together they form harmonies across space, layers of motion echoing through billions of light years. And though we can't hear it, this motion has a kind of tempo. It's the cadence of creation, steady and eternal. If you were to speed up the timeline of the universe until billions of years passed in seconds, you'd witness this hidden music visually. Galaxies would spiral like spinning notes, clusters would sweep together, filaments would glow and stretch, and the whole cosmic composition would pulse like a heartbeat. Each vibration of gravity, each ripple through space, would carry the same rhythm that began when the universe was young. Dark matter doesn't just structure motion, it gives the universe coherence. Without it, galaxies might still exist but scattered and fragile, unable to hold their form. There would be no great clusters, no cosmic web, no recognizable architecture at all. Dark matter is what ties every movement into a larger pattern. It is the unseen conductor guiding the orchestra, ensuring that chaos produces harmony. Even the smallest details echo this connection. The Milky Way's motion, for instance, isn't random. Our galaxy is slowly being drawn toward its neighbour, Andromeda, as both fall through the shared gravity of their dark matter halos. Beyond them, the local group drifts toward the Virgo cluster, and beyond that still, everything moves toward a region known as the Great Attractor, a dense concentration of galaxies and dark matter hundreds of millions of light-years away. Like dancers linked by invisible threads, each step in this motion traces the pull of the unseen. And while we often think of the universe as silent, that silence hums with energy. Every gravitational tug sends waves through space, subtle ripples that stretch and compress the fabric of reality itself. We've only just begun to detect them, gravitational waves from colliding black holes and neutron stars, but they're reminders that motion leaves music behind. On a cosmic scale, the universe truly hums in silence, guided by a force we cannot see. In computer simulations, this invisible symphony comes alive. Scientists can watch entire universes evolve, their dark matter scaffolds pulsing and flowing like sound waves turned visible. Galaxies form where the notes crescendo, where density builds and gravity swells. When they play these simulations back, frame by frame, the effect is mesmerizing. It's as if the universe is breathing, inhaling structure and exhaling light. Even the tiniest galaxies, faint and fragile, are part of this harmony. Some are like whispers on the edge of the cosmic song, small collections of stars circling within halos that outweigh them by thousands of times. Others are grand spirals, luminous symphonies of motion sustained by the dark matter beneath them. Each galaxy, no matter how humble, contributes its own rhythm to the whole. Dark matter's influence also shapes the paths of light itself. As galaxies move and cluster, their gravity bends space, distorting the light that passes through. To astronomers, this lensing effect is like hearing an echo, a faint reflection of the underlying melody. By studying those distortions, we can trace the contours of dark matter's rhythm across the sky. Mapping the hidden choreography that guides it all, it's humbling to realize how interconnected everything is. The same gravitational web that moves entire clusters also shapes the motion of our own galaxy, our solar system, even the trajectory of Earth itself. Every orbit we know, from the Moon circling our planet to the Milky Way circling the Virgo cluster, belongs to a greater pattern of motion. The universe doesn't move in fragments, it flows as one. If we could somehow step outside of it all and look back, the view would be astonishing. You'd see not a random sprawl of galaxies, but a graceful, coordinated dance. Threads of motion weaving together across the cosmic stage. Gravity would be the music, matter the melody, and dark matter the unseen score keeping everything in time. And yet, for all its precision, there's a softness to this cosmic choreography. The motions are so vast, so slow, that they unfold almost imperceptibly. To the human eye, the night sky looks still. But that stillness is an illusion. Every star you see, every galaxy glowing faintly in the dark, is moving in silent rhythm, following gravitational patterns written billions of years ago. The more we study this motion, the more we see its quiet elegance. It's not chaos that rules the universe, but balance. A deep mathematical harmony expressed through movement. Each orbit, each drift, each spiral contributes to the grand symphony of existence, and though we can't hear it, we can sense its presence in every corner of the sky. The cosmos hums in silence, guided by a force we cannot see. Its rhythm moves galaxies, its melody binds stars, and its harmony connects every atom to the whole. The music has been playing since time began, and it will continue long after the last star fades. Somewhere in that soundless song lies the reason the universe holds together, a reminder that even the quietest forces can create the most beautiful patterns. For all the brilliance of modern astronomy, the space telescopes, the supercomputers, the equations that map the birth of galaxies, there is still so much we do not know. We have measured the age of the universe with astonishing precision, traced its history from the first light of the cosmic microwave background, and charted the positions of billions of galaxies across unimaginable distances. Yet, after all that progress, the vast majority of the universe remains invisible to us. The cosmos, for all its beauty, still keeps its secrets. Dark matter is one of the greatest of those secrets. For nearly a century, astronomers have followed its clues, from the high-speed galaxies of Fritz Zwicky's Coma cluster to Vera Rubin's elegant rotation curves. We've built detectors deep underground, launched telescopes into orbit, and written equations that stretch the imagination. And still, dark matter has not revealed itself. It moves the universe, but refuses to be seen. It's easy, perhaps, to find that frustrating. Decades of research, billions of dollars, thousands of minds, all chasing something that refuses to cast even a shadow. But that quiet defiance is part of its power. The mystery of dark matter reminds us that science isn't a monument to certainty. It's a living conversation with the unknown. Every generation of astronomers inherits questions that cannot yet be answered, and in trying to solve them, they discover entirely new ones. This is how knowledge grows, not in a straight line, but like a spiral, circling closer to truth with every pass. Each experiment, even when it fails to find what it seeks, reshapes the path forward. When an underground detector records only silence, that silence speaks volumes. It tells us what dark matter is not. When cosmic surveys reveal patterns of galaxies that fit certain models and not others, the contours of the possible narrow a little further. Science, at its heart, is not about knowing everything, it's about learning which questions are worth asking next. For now, dark matter remains unseen, and that's all right. Its invisibility isn't a failure of science, it's an invitation. It calls us to look deeper, to refine our instruments, to stretch our imagination beyond the comfortable edges of what we can measure. The universe has never promised to be easy to understand, only that it would reward those who keep trying. When astronomers point their telescopes toward the faintest galaxies or the most distant quasars, they are looking into time itself, back to an era when dark matter first began to shape the cosmos. The light they capture has travelled for billions of years, crossing the invisible filaments that connect clusters and halos. Each photon that reaches us carries the memory of that hidden architecture. We can't see the dark matter directly, but we can see what it has made possible. The galaxies, the stars, the very conditions for life. The humility that comes from such understanding is a beautiful thing. It reminds us that even our greatest discoveries sit atop oceans of mystery. For every question answered, a dozen more arise, like stars appearing one by one as the sky darkens. The edge of knowledge isn't a boundary we can reach. It's a horizon that moves with us, expanding as we do. There's comfort in that horizon. It means there will always be something to seek. The physicists and astronomers who spend their lives chasing the unseen are not discouraged by what they don't know. They are inspired by it. Each unanswered question is another star we can aim for. The pursuit itself becomes a kind of light, faint but steady, guiding us forward through the cosmic dark. It's worth remembering how far we've already come. Not long ago, we didn't know that other galaxies existed, that the universe was expanding, that black holes were real, or that planets orbit stars beyond our own. Each of those truths once lived at the same frontier of mystery where dark matter resides now. What seems unknowable today may one day become textbook knowledge. The sort of fact students recite without realizing how extraordinary it once was. Perhaps that's what makes science so deeply human, its combination of wonder and humility. To study the universe is to stand before something immense and admit that we only see a fraction of it. Yet we keep looking anyway, not out of arrogance but out of curiosity. The same curiosity that first made someone look up at the night sky and wonder what the stars were made of. The unanswered questions do not diminish us, they define us. They remind us that discovery is not about possession, but perspective, the ongoing effort to understand our place in something larger. In a sense, dark matter is not just a scientific mystery, it's a metaphor for all that lies beyond our comprehension. We know it's there, we feel its influence, but we can't yet describe its nature. And still, we keep listening for its whisper. In quiet moments, when telescopes rest and the night sky is still, one can almost sense the weight of that unknown pressing gently on the imagination. The galaxies above, the atoms within us, the invisible scaffolding holding it all together, all of it part of the same unbroken story. To be human is to live inside that story without knowing how it ends. The pursuit of dark matter is a kind of dialogue between what we can see and what we can't. Each observation is a question sent into the dark, and each unanswered silence is the universe's way of saying, "Look again, try differently, think wider. There's something here. You just haven't found the right language yet." And perhaps that's the truest beauty of all. The universe does not reveal its secrets easily, but neither does it hide them out of malice. It allows us to find them slowly, as if teaching us patience, perspective, and awe. In its mystery, there is generosity. When we finally do uncover the nature of dark matter, whatever it turns out to be, it will not be the end of the story, only another beginning. The moment one curtain lifts, another appears behind it, shimmering faintly in the light of new knowledge. That's how science moves, one discovery at a time, always toward the next unknown. So we stand here on our small planet orbiting an ordinary star surrounded by mysteries older than time, and we keep asking questions. We look at the night sky not for answers alone, but for the joy of the asking. Because in every unknown there's something sacred, a reminder that we are part of a universe vast enough to outthink us, yet kind enough to let us try. We don't know what dark matter is, not yet. But the search for it has shown us something equally important, that wonder itself is a form of understanding. The unknown is not an obstacle, it's the reason we keep exploring. And so, with gratitude for the mysteries that remain, we continue the journey. Eyes open to the dark, hearts lifted toward the horizon, ready to follow every unanswered question like another star we can aim for. For something we can't see, dark matter has been remarkably generous. Without it, there would be no galaxies, no stars, no planets, and certainly no life. Everything luminous, every atom, every spark of light in the night sky owes its existence to this invisible framework. It is the quiet architect of the cosmos, the unseen hand that drew the outlines of everything that came after. To understand why dark matter matters, it helps to rewind the story of the universe to its earliest chapters. In the moments after the Big Bang, the cosmos was a near-perfect soup of energy and particles, uniform, smooth and expanding. Ordinary matter, the stuff made of protons and electrons, was trapped in a fiery dance with radiation, constantly colliding, scattering and refusing to settle. On its own, it could never have formed the dense clouds needed to make stars. Gravity tried to pull things together, but the pressure of light pushed them apart just as quickly. Dark matter, however, was different. It didn't interact with light at all, which meant it could start clumping long before everything else. As the universe cooled, it began to gather into vast halos, invisible wells of gravity, shaping space without shining. When ordinary matter finally broke free from radiation, it drifted into these wells, collecting in their depths, cooling further, and eventually igniting as the first stars. Those early stars went on to forge the heavy elements, carbon, oxygen, iron, the raw ingredients for planets and people. Every breath we take, every cell in our bodies, was once part of a star that formed, because dark matter gave gravity a head start. Without that invisible scaffolding, there would be no places for light to gather, no galaxies to spin, and no worlds to host the story of life. It's humbling to think that we owe our existence to something that never shows up for photos. It doesn't sparkle, it doesn't glow, and it doesn't seem to care whether we ever find it. Yet without its silent gravity, the universe would be little more than an endless cloud of hydrogen, drifting aimlessly in the dark. Stars would never have ignited. The night sky would be truly empty, not a canvas of beauty, but a blank page. Dark matter doesn't just explain how galaxies formed, it also keeps them together. The stars in the outer reaches of a spiral galaxy move too fast to be held by visible mass alone. Without the extra gravity supplied by dark matter, they would drift away like sparks from a fire scattering into space. The very shape of galaxies, their elegant spirals and glowing cores, depends on the invisible halos surrounding them. Even now, our Milky Way is cocooned within a vast bubble of dark matter stretching hundreds of thousands of light years in every direction, holding everything in balance. It's strange to think of something so intangible being so essential, but that paradox, the visible resting on the invisible, runs through nature at every scale. We see the waves, but not the gravity that pulls them. We feel warmth, but not the fusion that creates it. We witness life, but rarely consider the chemistry quietly working behind it. The cosmos itself is built on this pattern, the seen emerging from the unseen. In a way, dark matter is the universe's most profound metaphor. It reminds us that what matters most isn't always what we can see. Our world is shaped by invisible forces, gravity, air, time, thought, each as real and powerful as the stars themselves. Dark matter is the grandest version of that truth, a cosmic embodiment of the idea that the unseen often holds everything together. Even on human scales, that lesson resonates. The things that bind us, love, memory, curiosity, can't be weighed or photographed, yet they hold entire lives in orbit. In a universe built on invisible foundations, it feels fitting that our own stories are held by unseen forces too. Dark matter's quiet role also offers a sense of perspective. It reminds us that the universe isn't built for visibility. Most of its mass, energy, and structure exist beyond what human senses can perceive. Our eyes are tuned to a narrow slice of light, our instruments to a few ranges of energy, and yet we sometimes imagine that what we see is all there is. Dark matter humbly corrects that illusion. It whispers that the real story is deeper, that the universe is more mysterious, more layered, and more generous than it appears. Even now, billions of years after those first halos formed, dark matter continues to shape cosmic destiny. It dictates how galaxies cluster, how they move, how they merge. It pulls filaments into alignment across the cosmic web, guiding everything from the motion of galaxy clusters to the very expansion of the universe. When astronomers trace the large-scale structure of space, they are mapping not stars, but dark matter's ghostly influence. Every spiral, every cluster, every cosmic filament is a kind of sculpture carved by invisible hands. Our place in this story is both small and miraculous. We live in a galaxy held together by dark matter, orbiting a star born from gas that fell into a dark matter halo billions of years ago. The atoms in our bodies trace their lineage to that ancient gravitational pull. In a very real sense, we are children of the unseen, made possible by something we can't yet comprehend. It's tempting to imagine what it might feel like if dark matter were visible, if its structure glowed faintly, outlining the universe in threads of light. The night sky would no longer seem vast and empty. It would shimmer with the interconnectedness of everything. Perhaps then we would better grasp how extraordinary it is that the cosmos, in all its silence and scale, came together at all. There's also something quietly poetic about our dependence on something so mysterious. It's as though the universe wanted to remind us that not everything essential can be directly known. Dark matter, in its perfect restraint, gives space to all the light and colour of creation. It supports the visible without competing with it, shaping without showing, guiding without demanding recognition. And that's what makes it beautiful. Its invisibility isn't absence, it's presence of a different kind, subtle, patient, and profoundly effective. The universe doesn't need to shout to be magnificent. Sometimes the greatest forces are those that stay silent, letting their influence speak through what they make possible. Every star that shines tonight, every galaxy drifting serenely through the cosmic web, is a monument to that invisible grace. Dark matter's pull has written the structure of the heavens, but it has also written our story. The atoms in our blood, the earth beneath our feet, the light that warms our skies. It shaped the stage long before the play began, so when we look up and marvel at the stars, we're really seeing the faint reflection of something deeper, the quiet architecture that made those stars possible in the first place. We may never see dark matter directly, but we live inside its legacy. It surrounds us, sustains us, and keeps the universe in balance. We owe our existence to something that never shows up for photos, the shy builder behind all that is bright. And perhaps that's the most poetic truth of all. The cosmos, from its grandest clusters to its smallest cells, runs on a principle as old as time. The invisible gives shape to the visible. The unseen has always held more power than we realize. If the story of dark matter teaches anything, it's that the universe rewards curiosity and humility in equal measure. It's a story that began not with certainty, but with confusion. A few galaxies moving faster than they should, a handful of astronomers noticing something didn't quite fit. From those quiet puzzles came one of the grandest realizations in science, that most of the cosmos is invisible. The stars we see, the nebulae we admire, even the luminous arms of galaxies. They are all just the frosting on a vast and hidden cake. It started, as so many great scientific adventures do, with someone daring to ask a question no one else was asking. In the 1930s, Fritz Zwicky looked at the Coma cluster and saw galaxies whirling at impossible speeds. His calculations told him something was missing, a hidden mass holding everything together. Few believed him then. He was brilliant but blunt, famously difficult, and perhaps too far ahead of his time. Yet history has a way of catching up to the stubborn. Decades later, Vera Rubin turned her telescope towards spiral galaxies and found the same whisper that Zwicky had heard. Stars on the outskirts moving too quickly for visible matter to explain. She wasn't trying to rewrite cosmology. She was simply following the data night after night with quiet persistence. The pattern she uncovered became undeniable. Galaxies were not bound by what could be seen. The invisible was shaping everything. From there, the story unfolded outward, from galaxies to clusters, from clusters to the vast cosmic web. Each discovery added another layer of wonder. Astronomers mapped the filaments of dark matter that thread the universe, simulated its formation on supercomputers, and measured its gravitational pull in light that bends and warps across billions of light years. What began as a single anomaly in a cluster of galaxies became a new way of seeing reality. The search for dark matter is more than a hunt for particles. It's a meditation on perspective. It reminds us that our senses, for all their beauty, only skim the surface of truth. We see light, but light is just a sliver of what exists. The universe is richer, deeper, and more intricate than we can ever fully perceive. A masterpiece painted mostly in invisible strokes, and yet, for all our limitations, we've managed to glimpse its shape. Through the faint bending of light, through the motion of stars and galaxies, through the structure of space itself, we've mapped the outlines of an unseen world. That alone feels like a small miracle, that a species made of stardust, living on a tiny planet around an ordinary star, could reach across billions of light years to infer the architecture of the cosmos. Science and imagination, often seen as opposites, meet perfectly in this mystery. To explore something that cannot be seen demands both the rigor of mathematics and the courage to dream. Every theory, every model, every simulation is an act of creativity as much as calculation. The universe invites us to reason deeply and to wonder endlessly, never fully separating the two. Dark matter in this sense unites the poetic and the empirical. It is the bridge between what we know and what we can only imagine. We understand its gravity, its influence, its fingerprints, and yet its true nature eludes us. It sits quietly at the border of knowledge, both known and unknown, real and mysterious. That paradox is what keeps science alive. It's easy to think of science as a march towards certainty, but dark matter reminds us that its heart beats to a slower rhythm. It's not about having all the answers, but about finding better questions. Each discovery opens new doors, and behind each door lies another mystery waiting patiently in the dark. The joy isn't in finishing the story, it's in realizing the story has no end. There's something profoundly comforting about that. To live in a universe that still holds secrets means we are not done learning. The unknown isn't an absence of understanding. It's an invitation to explore. It keeps us humble, reminding us that no matter how advanced our instruments or precise our equations, we remain students of something infinitely larger than ourselves. And in the end, perhaps that humility is the real gift of dark matter. It reminds us that not every truth must be visible to be real, and not every mystery demands resolution. The cosmos isn't a puzzle to be conquered. It's a relationship to be tended, a dialogue between curiosity and wonder. If we could speak to Zwicky or Rubin today, perhaps they would smile at how far their questions have travelled. Their observations, once controversial, have become the foundation of modern cosmology. Yet even now, with all we've learned, the central question remains: what is dark matter? And perhaps the deeper question: why does it exist at all? Maybe the answer will come from a particle accelerator or an underground detector or a new kind of telescope that sees what we cannot. Or maybe it will remain elusive for centuries, a silent reminder that some truths prefer to stay mysterious. Either way, the journey toward understanding it has already enriched us. It has deepened our view of the universe and, in turn, our view of ourselves. Because when we gaze into the night sky, we're not just looking outward, we're also looking inward, tracing our own origins back to the forces that shaped us. The same invisible gravity that binds galaxies together also binds our atoms, our histories, our hopes. We are made of the visible, but guided by the invisible. Perhaps that is the quiet revelation at the heart of dark matter's story, that the universe doesn't need to be fully understood to be beautiful. Its mystery is not a flaw, but a feature, a reminder that reality can still surprise us. The unseeable can be just as vital as the seen, the questions just as sacred as the answers. And so, as the search continues, from observatories deep underground to satellites far above the Earth, we can take comfort in what we've already found, a sense of awe, a connection to the cosmos, and a deepening respect for the vastness of what remains unknown. The unseen scaffolding of the universe may never reveal its true nature, but in striving to understand it, we reveal something about ourselves, our curiosity, our persistence, our capacity to wonder. The story that began with a few puzzled astronomers now belongs to everyone. It's written in the light of galaxies, in the silence between stars, in the collective human desire to understand what holds the universe together. And perhaps that desire is itself a kind of gravity, an invisible force drawing us towards knowledge, one question at a time. We may never know exactly what dark matter is, but that doesn't diminish its beauty. The unknown, after all, is not the enemy of understanding, it's the foundation of it. Every unanswered question is a spark of imagination. Every mystery a quiet reminder that discovery is still possible. In the end, the search for dark matter is the search for wonder, for the humility to admit that we are surrounded by forces we cannot yet grasp, and for the joy of realizing that this mystery, far from closing the book on science, keeps it endlessly open. The universe hums softly in its silence, shaped by an invisible hand, reminding us that some mysteries aren't meant to be solved, only appreciated. And in that appreciation lies peace, the quiet recognition that not knowing everything is part of what makes existence so extraordinary. What is dark matter? The honest answer remains both simple and profound. It is real as mathematics and unseen as light. We do not see it shine. We do not feel it on our skin. We cannot hold it in a jar or press it into a photograph. And yet its gravity writes the motions of galaxies, sculpts the filaments of the cosmic web, and anchors the architecture of everything we can see. It is presence without colour, weight without glow, the quiet half of the universe's story. We came to this answer slowly, in the way science often moves, circling truth with patience. A Swiss astronomer added up the speeds of galaxies and found more gravity than stars could supply. A careful observer measured how spiral galaxies spin and discovered their edges refusing to fade. Light from distant quasars bent into crosses and arcs, tracing mass that no telescope could capture. Clusters collided and their luminous gas lagged behind while the gravitational centers marched ahead. Again and again the evidence pointed to the same conclusion. The luminous world rides on an invisible sea. Over time, that realization changed how we see everything. Galaxies no longer solitary pinwheels, but lanterns drifting inside vast halos. Clusters do not float randomly, but slide along dark strands stretched across space. The early universe was not a featureless fog. Faint ripples grew into structure because unseen matter gathered first, making wells for ordinary gas to fall into and ignite as stars. What we call darkness, it turns out, is not emptiness. It is scaffolding. We have given this scaffolding a name, and then we asked it for its identity. Are you heavy, like a rare and quiet particle? Are you featherlight, like a sea of axions humming softly through the cosmos? Are you something stranger, some subtle twist in gravity itself? We built detectors in old mines, cooled instruments until the atoms barely trembled, launched observatories that listened for the faintest whispers in gamma rays and antimatter. The most common result has been silence, but even silence trims the marble. It tells us where not to look and how to listen better. Not knowing everything does not make science weaker. It makes it deeper. It forces us to refine questions, to separate what we hope from what the universe is willing to say. The unanswered keeps curiosity alive. It reminds us that knowledge is more horizon than finish line. Each limit we set, each model we rule out, each map we sharpen adds contour to the invisible. Discovery is not only the moment of yes, it is also the long, careful no that clears space for the right answer to appear. There is gentle humour to the cosmos in all of this. We spent centuries becoming experts at light, splitting it into colours, measuring its speed, catching it from the first moments after the Big Bang, only to learn that most of the universe does not bother with it. The universe keeps a few secrets just to keep us curious, and in that playful restraint is an invitation. If we want to understand the whole, we must learn to read what light bends around, not only what it illuminates. In the meantime, dark matter continues its work without waiting for our understanding. It steadies the outer stars of our Milky Way. It threads our local group to its neighbours. It holds clusters in their slow embrace and lifts bridges between them. It shapes the stage on which every luminous event occurs, supernovae blooming and fading, planetary systems assembling, life taking root on worlds warmed by ordinary suns. We are the bright embroidery on an older, darker cloth. There is also a lesson here about seeing. What matters most is not always what meets the eye. Air is invisible and essential. Gravity cannot be seen, only felt through falling apples and circling moons. Love, memory, meaning, all of them unphotographable and yet powerful. Dark matter is the cosmic echo of that truth. The visible world rests on an invisible foundation, and the foundation does not complain about credit. One day, perhaps, we will give the mystery a face. A crisp signal will stand above the noise. A new kind of detector will catch a rare collision. A clever idea will turn a faint hint into clarity. Or perhaps the answer will be stranger than any of our categories. Either way, the search will have been worth it, because along the way we built instruments of exquisite sensitivity, mapped the large-scale structure of the universe, and learned, again, that humility is part of wisdom. As this journey pauses, take a last look at the thread we followed. A puzzled calculation in a galaxy cluster. A patient set of rotation curves. The delicate smudges of weak lensing across deep surveys. Collisions in the sky that separated light from gravity. Simulations blooming like frost into filaments. Quiet laboratories waiting for a particle to tap on the door. Together they tell a single, steady story. Something unseen holds the cosmos in its hands, so we'll keep asking and the universe will keep answering in its own measured way. We will keep mapping what we cannot see, listening for what we cannot hear, making peace with the fact that mystery is not a failure but a feature, the depth that gives meaning to the surface. For now, let the question rest gently. What is dark matter? It is the name we give to the gravity that exceeds the light, the framework we infer from the motion of things, the unseen partner in a dance that began when time was young, real as mathematics, unseen as light, and patient enough to wait while we learn. As you drift to sleep, remember, even the darkness between stars is full of meaning. It holds the cosmos together, quietly, completely.